In this learning path, we will cover the building of blockchain networks and blockchain applications on the cloud. To get the best out of the courses in this path, however, there are a few prerequisites, both in terms of theoretical knowledge as well as hands-on skills. First of all, you need to have a fundamental understanding of blockchain technology. Since we will be building blockchain networks, as well as deploying smart contracts and building applications on top of them, it'll greatly help if you have already come across blockchains before and have built and deployed smart contracts on your own. In addition to knowing about blockchains, it'll also greatly help if you have some familiarity with cloud computing. In this learning path, we will be making use of the Amazon Managed Blockchain Service, which is available in AWS, and this will require setting up of a number of different AWS resources. We will also be making use of Microsoft's Azure in order to use their Azure Blockchain Workbench service. So if you will be looking at the courses involving those services, then having some prior experience using each of those cloud platforms will greatly help. And finally, you need to have some degree of experience with both application development as well as using the Linux command line. We will be coding smart contracts for both the Amazon Managed Blockchain Service as well as the Azure Blockchain Workbench, and will also be executing several commands in order to set up and then manage the blockchain networks. So some prior coding experience as well as familiarity with the Linux shell will allow you to focus on the new concepts introduced in this learning path and get the most out of each of the courses. So let us dive right in and then explore how it helps to build blockchain networks and applications on the cloud. First of all, we take a look at what exactly a blockchain is. One definition is that it is essentially a list of records which are stored across a sequence of blocks, and these blocks happen to be chained together using cryptography. We can now break down this definition into its components. Firstly, that a blockchain is a list of records which stores some data. All of this data is stored across a collection of blocks, and these blocks are arranged in a sequence, and this is accomplished by means of chaining them together. We can now visualize what a blockchain looks like by starting off with a list of 9 records. So consider that this is the data which you need to store in a secure manner. Not only should the data be secure, but the ordering of the records must also be preserved. So in this case, we have 9 records, each of which have a sequence number 0 through 8. The way blockchains store this data is by first splitting them into blocks. So consider that the first 3 records are in block number 1 here, the next 3 are in block number 2, and then the remaining 3 records are in block number 3. You will notice that within each of the blocks, the ordering of the records has been maintained, and in order to maintain an overall ordering of the blocks themselves, these blocks are chained together. So block number 1 is connected to block number 2, and then number 2 is connected to the last of these blocks. And the way this chaining is accomplished in a blockchain is by means of a cryptographic link. How exactly is this cryptographic link implemented? Well, for that, each block contains a number of pieces of data. One of these is the cryptographic hash of the previous block in the blockchain. In addition to this, a block may also include a timestamp, which denotes when exactly that block was added to the blockchain. There is, of course, the important transaction data or the records which are stored on the blockchain. And then in addition to that, in order to make it easier to access the information, there may also be some metadata. So depending on the blockchain implementation, there may be additional data in a block as well. However, in any case, all of the data which makes up the block, including the fields which you see right here, will be fed into a cryptographic hash function, and the output of that cryptographic hash will be included in the next block of the blockchain. It is this hash which forms the cryptographic link connecting each of the blocks in the blockchain together. So what exactly is the purpose served by this cryptographic link? Well, one task which is accomplished is that it ensures that the transaction data in any block cannot be altered once it has been written to the blockchain. If a malicious entity were to try and edit one of the transactions which were written to one of the blocks, they will not only need to alter the block containing the transaction, but all of the subsequent blocks in the blockchain. This is an operation which will require consensus from all of the other nodes which are participating in a blockchain network, since they will recognize that the hash of the block containing that transaction will have changed. In order to make a change to a transaction which goes undetected, the malicious entity will then need to ensure that the hash of that block does not change. And since a hash output cannot really be reverse engineered, this is not exactly a feasible operation. So the existence of this cryptographic link in any block of the blockchain serves two purposes. Firstly, it ensures that every transaction recorded on the blockchain is both verifiable and also immutable. And these are precisely what make blockchains a secure place in which to record transaction data. To understand exactly how this cryptographic link prevents tampering, we can take a look at an example. So consider here that we have three different blocks of transactions, and each block, of course, contains the hash of the previous block in the blockchain. This does not apply to the first block in the chain, which is the genesis block. Now, consider an example where some malicious party tries to alter one of the transactions in block number 1. When this change is made, then the hash of this first block will have changed. And since that hash is included in the second block, then the second block will also change along with its hash. This will mean that block number 3 will also need to change, and this will in fact go on until the end of the blockchain. Since multiple nodes in the blockchain network will have their own copy of the blockchain, any malicious party trying to modify their own copy will have a blockchain which is very different from that of the other nodes in the network. We can also assume that this malicious entity will not be able to alter the contents of a block without modifying the block hash, since a cryptographic hash cannot really be reverse engineered. What all of this boils down to is that there is no way for someone to tamper with the blockchain and not get caught, since even a tiny alteration to one of the transactions will result in a vastly different blockchain which will be detected by the other nodes in the network. What all of this means is that blockchains are a secure place in which to record transaction data. So if you see any information on the blockchain, then you can rest assured that it has not been tampered with from the time it was written. But how exactly do we write data to a blockchain? One way to do this in many blockchain implementations is by means of a smart contract. This can be defined as a protocol to digitally specify, verify, and potentially even enforce the terms of a contract. Exploring some of the properties of smart contracts, the first thing we should mention is that this is where contractual terms are specified in code rather than in legal terms. One aspect which distinguishes smart contracts from the traditional ones is that there is no ambiguity in the digital versions. You can take a look at the code and know exactly how a smart contract will be executed, and there are no gray areas here. Additionally, smart contracts are both immutable and also distributed by virtue of being on a blockchain network. So there is no single party which will be controlling a contract at any point in time. And the true power of smart contracts lies in the fact that they can greatly minimize third-party involvement in many different interactions. In the previous video, we covered the fact that blockchains offer a secure place in which to record transaction data. We will now take a look at some of the blockchain-based solutions which are out in the market, and will also explore some of the pros and cons for each of them. So let us now quickly summarize some of the benefits of blockchain networks make for an ideal place in which to record transaction data and why many organizations are beginning to adopt this technology. First of all, blockchain networks are distributed across multiple nodes. This means that the data on a blockchain is not controlled by a single entity, and there will be some consensus required among all of the nodes in the network before data can be written to it. Secondly, the data, once it has been committed to the blockchain, cannot be modified. That is, it is immutable. And if you see some data on a blockchain, then you can rest assured that it has not been tampered with. Also, since each record affects the hash of the block to which it belongs, as well as the hash of all of the subsequent blocks, this means that every record is verifiable. A combination of these properties means that the data which you see on a blockchain can be entirely relied upon, and it is this ability to trust the data which makes blockchain technology the ideal solution for many organizations who wish to record transactions with parties they don't entirely trust. Another crucial feature of many blockchain networks, which involve smart contracts, is that these contracts tend to minimize third-party involvement in many different interactions. Smart contracts can be coded up in such a way that the role of a trusted third party is played by the contract itself. And once again, given the digital nature, the behavior of the contract is both predictable and unambiguous. So now that we have established that blockchain networks can be an ideal solution in many different cases, the question is, what are the different types of blockchain networks which are available for users? What are the different implementations which are out in the market? Well, there are a number of different options available, but we can now take a look at some of the more popular ones. Out of the public blockchain networks, that is, networks which anyone is free to join, there is Bitcoin, which in many ways can be considered the pioneer of blockchain technology. And then there is also the widely used Ethereum network. Both of these are specific examples of public blockchain networks. And we can now take a closer look at some of their properties. As touched upon, public blockchains are those which anybody is free to join, as long as you have the hardware and the required software. There is no invitation involved or even a vetting process, so the barrier to entry into such networks is indeed really low. As a consequence, though, these networks tend to be very large and involve several thousand nodes. A positive effect of this fact is that it is very difficult for a single entity to take control of the entire network. On the other hand, it does make the network much more complicated to manage. Another feature of public blockchain networks is that since they are public, all of the transaction data is available for all to view, and depending on the implementation, multiple nodes in the network will have access to the smart contracts as well. Though it is possible for users to hide their identities behind account numbers, any transactions which are recorded on this network will be public, and this is not the place in which to record private transaction data. One side effect of having several thousand nodes, none of which have been properly vetted, means that there needs to be some kind of consensus mechanism which makes it possible for the network to function in spite of having some malicious nodes involved. Though to a great degree the public blockchain implementations manage to accomplish this, this usually comes at the cost of performance, and this is something we will explore in a little more detail in just a little bit. So now that we have an idea of what public blockchain networks are, we will take a look at the specific examples we touched upon just a little earlier, starting with the Bitcoin network. And the question to pose now is the Bitcoin network the ideal solution for end users and organizations in which to record their transaction data? Well, the answer in this case is no. There is really just one type of transaction which the Bitcoin network can record, and this involves the transfer of its own cryptocurrency from one Bitcoin account to another. Many users of blockchain applications will not want anything to do with cryptocurrencies. All they want is to record their own bespoke transactions on the blockchain. The way to define these bespoke transactions is by means of smart contracts, and as of this recording, this is not a feature which is available on the Bitcoin network. So with the Bitcoin network, we really are only limited to one type of transaction and have no option to define our own. This rules out the Bitcoin network as a solution for end users or organizations which wish to record their transaction data on a blockchain. What about the Ethereum network though? At the time of this recording, Ethereum is certainly the most mature public blockchain network available for users and also happens to be very widely used. The main reason for this is that Ethereum supports the notion of smart contracts. So end users will be able to define their own transactions within these contracts and then record those transactions on the blockchain. So with this feature, Ethereum distinguishes itself from the Bitcoin network and also makes it a viable solution for users and organizations to record their transactions. One thing to keep in mind, however, is that much like the Bitcoin network, Ethereum also uses its own cryptocurrency, and this is known as Ether. As I had mentioned previously, many users of blockchain solutions don't want any interaction with a cryptocurrency. However, they may be willing to put up with it if there are several other features which are offered in the network. And the option of having smart contracts definitely makes Ethereum a potential blockchain solution. However, there are several restrictions which prevent the widespread adoption of Ethereum by enterprises. For any large organization which will have many transactions involving several parties, an important factor to consider when using any solution is the ability to scale. And as of this recording, this is definitely a negative factor when it comes to the Ethereum network. The number of transactions which the Ethereum network can handle is merely a fraction of what even a single organization would require. Additionally, the resource utilization on Ethereum is far from efficient, and this once again is a huge factor when it comes to enterprises adopting the technology, since any organization will want to make the best use of all of their hardware resources available. And finally, another practical limitation of the Ethereum network is the fact that it does not allow for confidential transactions. All transactions are available for anybody to view, not just members of the network. And while transparency is desirable in many different situations, it is not always the case in business. So, to sum up, it is these three big factors which are holding back the adoption of Ethereum as a blockchain solution for organizations. In the next video, we will take a closer look at each of these limitations and will also explore the properties which make for an enterprise-grade blockchain solution. In the previous video, we covered the fact that the adoption of Ethereum as an enterprise-grade blockchain solution has been limited by concerns around its ability to scale, its resource utilization, and also the confidentiality of transactions. But to understand exactly why these are limitations, we can take a closer look at each of these concerns, starting with the inability of the Ethereum network to process many transactions. That is, the inability to scale. As of this recording, the throughput of the Ethereum network is just about 3 million transactions per day. This is for the main Ethereum network, which is supposed to be the single blockchain on which the whole world records their transactions. 3 million transactions per day is often not enough for even one large organization such as a bank or a credit card company, let alone the entire planet. And the reason why Ethereum is not able to scale up even more is mainly to do with the time it takes to verify transactions. Given there are thousands of nodes in the network, many of which cannot really be trusted to behave correctly, Ethereum adopts the proof of work algorithm for consensus, and this is very time consuming and prevents Ethereum from scaling up much more beyond 3 million transactions per day. Which takes us to the other side effect of the proof of work algorithm, which is around resource utilization, and there is a lot of wasted effort among the nodes in the Ethereum network as a result of this consensus mechanism. Thousands of nodes which make up the Ethereum network end up expending a lot of electricity for the purpose of mining. And while this mechanism does prevent fraudulent nodes from taking over the network, it does come at the cost of very large electricity bills, which many regard as a highly inefficient way in order to secure the network. Ethereum has been actively looking into alternatives to the proof of work algorithm as a result, and one of the contenders is the proof of stake. And while this does address several of the issues around proof of work, it does come with several negatives as well. Specifically, it favors entities who have the ability to put up large sums of money. So it is more efficient but not as democratic as the proof of work. Which takes us now to the issue of security and confidentiality. As touched upon, the Ethereum network is very transparent in that anybody, whether you are part of the Ethereum network or not, will be able to view data related to transactions and contracts. This is because there is no mechanism in the network to regulate access to the transaction data, and this is not exactly a bug, but it is very much by design. This, however, is a deal breaker for many organizations, which may offer one rate for a particular product to one customer and a different rate to other customers. And they would like these rates to be available only to the parties directly involved rather than to the general public. One security risk in the Ethereum network and in public networks in general is that it is possible for a fraudulent entity to take over the network. As of mid 2019, this is not considered a likely scenario, but it is certainly something which is possible, and even a remote possibility can be considered too big a risk for many large organizations. So, with all of these limitations around Ethereum, it becomes clear that the public Ethereum network is certainly not a solution for many large enterprises. So, many organizations do like the fact that blockchain technology allows transaction data to be recorded in a tamper-proof manner, and that smart contracts do minimize the involvement of trusted third parties in many interactions. But what are the other features which they require? What makes for an enterprise-grade blockchain solution? Well, for one, it needs to have a high throughput. It at least needs to be able to record tens of millions, if not billions of transactions each day. In order to meet this throughput requirement, though, the transaction processing itself needs to be highly efficient, and transactions need to be processed within milliseconds or even nanoseconds. Another concern for enterprises is that the cost for using a blockchain solution should at least be predictable or potentially even free. The transaction fees on the Ethereum network can vary along with the price of the Ether cryptocurrency and also the demand on the Ethereum network at any given point in time. And this is a factor which many organizations would rather not have to worry about. An enterprise-grade solution will also make optimum use of the resources which are available. This often translates to all of the processing power being directed towards transaction processing rather than verifying whether a particular entity is behaving in a fraudulent manner. And this is something which can be addressed by having control over who gets to participate in the blockchain network. If there is some vetting process involved, then enterprises can ensure that there is at least some degree of trust in any participant in the network, and they don't need to constantly verify whether that entity is behaving correctly. Another nice to have feature in any blockchain solution is the ability to code up smart contracts in more widely used languages. Smart contracts on the Ethereum network, for example, need to be coded in a domain-specific language called Solidity, and it is often hard for organizations to find engineers who have any expertise in that particular language. On the other hand, it is much easier to find engineers who have experience in languages such as Python or Node.js. So, any blockchain solution which allows smart contracts to be coded in those languages is certainly more appealing than the Ethereum network. Additionally, To ensure confidentiality of transactions, it should be possible for an enterprise to configure the blockchain network. This includes details such as access control to regulate who has access to what in the network. Enterprises may also wish to control the specific security mechanisms which are implemented in the blockchain solution. For instance, this could include the encryption mechanism for network traffic. Enterprises may wish to use their own membership services in order to identify different entities participating in the network. For example, do you use certificates in order to establish identity? And if so, what are the trusted certificate authorities? Other details which can be configured include the consensus mechanism for a blockchain network. A plug-and-play consensus mechanism could make it possible for one solution to be implemented in a dev or test environment and a different, more robust solution in production. So with that, we now have an understanding that networks such as Ethereum offer a lot of the basic features which are required by enterprises to record transactions on a blockchain, but there are also several limitations which prevent it from truly being considered an enterprise solution. So, in order to build a blockchain solution which can be considered enterprise grade, there are two potential ways for us to approach the problem. One is to modify the Ethereum source code and then build a new consensus mechanism and make other modifications which address the issues which we have around its scalability, resource utilization, and also security and confidentiality. In fact, this is precisely the approach adopted by the Azure Blockchain Workbench. Another way to build an enterprise-grade blockchain solution is to come up with a brand new solution from scratch. And this is the approach adopted by Hyperledger, which has produced not one, but a number of different blockchain solutions. Out of the many Hyperledger blockchain solutions, it is Hyperledger Fabric which has been adopted by the Amazon Managed Blockchain Service. We will be taking a look at both of the blockchain solutions offered by Azure and Amazon a little more closely in the next video. In this video, we will take a look at why it makes sense for many enterprises to make use of one of the managed blockchain solutions which are offered on the cloud by cloud service providers such as Azure and AWS. We have previously covered the fact that there are several benefits of blockchain networks which make them an ideal place in which to record transaction data, and this is why many enterprises are beginning to adopt this new technology. Blockchains are distributed across multiple nodes so that their control is not limited to just a single entity. Data written to a blockchain is both immutable and verifiable, and many smart contracts can either minimize or even entirely do away with the involvement of trusted third parties for many different interactions. All of these features are offered by blockchain implementations such as the Ethereum network. However, there are several limitations associated with Ethereum which we had covered previously. So, in order to build an enterprise-grade blockchain solution, there are two possible approaches. One of these has been adopted by the Azure Blockchain Workbench, which is to modify the Ethereum source code, where you make use of the underlying features of the Ethereum blockchain, but then address some of the limitations. The other approach is to build a brand new solution, and this is one which has been used by Hyperledger, which has implemented not one, but a number of different blockchain solutions. Out of those, it is Hyperledger Fabric, which is the blockchain solution adopted by the Amazon Managed Blockchain Service. Each of these cloud services involves spinning up a private blockchain network using the resources available on that cloud service. Now consider the case where rather than using one of the managed blockchain services available on these cloud vendors, you try to set up a private blockchain network on your own. What exactly are the steps involved in this process? Identifying all of these steps will help you figure out how much simpler one of the cloud services makes it to set up the blockchain network and whether it makes sense for your organization to use one of those services. For this particular example, we can consider setting up a Hyperledger Fabric network from scratch using the available installation files. So in order to provision a blockchain network, you will first need to provision the nodes which make up the blockchain network and also deploy the network itself. These nodes can either be on-premises or even on the cloud, or potentially a hybrid solution, but how exactly those nodes are provisioned is something which you will need to take care of. As for setting up the network, the installation files will be available online and you can just download them and make use of them in order to set up the network. The installation, though, will also require some configuration files which you will need to define and then maintain over the lifetime of the network. In order to regulate access to the network, you will need to issue identities to the different participants, and the provisioning and distribution of these identities is something which you or your organization will need to handle on your own. Following that, in order to begin using the network, you will need to code up the smart contracts, and it will be up to you to code up these contracts from scratch and then deploy them to the network. You will likely need to code up an application which will make use of an intuitive user interface which can interact with the deployed contracts. For example, you may code up a web application to interact with a smart contract which has been deployed to either a Hyperledger Fabric or an Ethereum network. We can now take a closer look at each of these steps, starting with the provisioning of the nodes and the network. You will likely need to provision virtual machines for the different network components. This may include the clients, and in the case of the Hyperledger Fabric network, you could have different VMs for the certificate authority and also the ordering service. Along with the VMs themselves, you will need to ensure that they're able to communicate with each other by setting up your network accordingly. And it is then your responsibility to maintain both the nodes as well as the network. There will be more maintenance work involved if these nodes happen to be on premises rather than on the cloud, but in either case, there is a significant amount of effort required to maintain your blockchain network. Moving ahead now to the configuration files, this is where you may need to set up private channels in order to allow confidential transactions on your network. This is especially the case with Hyperledger Fabric. Each time a new channel needs to be created, it is up to you to edit these configuration files and then run the binaries to provision the channels. The config files can also include details such as the connection information for different components. For example, which host and port is the ordering service listening on. When setting up a blockchain network from scratch, these config files will need to be defined and then maintained by you and your organization. Moving on to the next step of managing identities, this may involve tasks such as issuing certificates to the different participants in the network and also handling the keys which will be used in order to encrypt traffic. These identities will also be used in order to assign permissions to the different participants in the network. The next step in the process is to develop smart contracts. This is where you can define the types of transactions which need to be recorded onto the blockchain and the details which are required in order to trigger those transactions. Once your contracts have been defined, you will need to deploy them to the required nodes in the blockchain network. With the setting up of the nodes, the channels, the identities, and the contracts, it is possible to begin interacting with the contract and record transactions on the blockchain by using some kind of client and then using the command line in order to trigger the transactions. However, it will be much easier from the user's perspective if there was an intuitive user interface for this purpose. So you will very likely need to build and then maintain a web application for this purpose. A UI is a must if your organization has several non-technical users who cannot be expected to invoke transactions from a shell. In fact, even for technical users, a web application is just more convenient and intuitive. So we have now covered 5 broad steps which are required in order to set up and begin using a blockchain network to record transactions. In short, it is now clear that building and maintaining a blockchain network is quite complicated. However, does this really need to be the case? Going back to the 5 different steps which we have just covered, is there any way for this process to be simplified? Well, the short answer is yes. And this is precisely where the managed blockchain solutions come into the picture. The two managed blockchain solutions we will be focusing on in this learning path include the Azure Blockchain Workbench and the Amazon Managed Blockchain, which is offered on AWS. What these two services essentially say to their users is that you can focus on building the logic for your blockchain applications and on building your smart contracts and leave the scaffolding to them. What this boils down to is that all of the nodes and the networks are provisioned and maintained on the cloud. You don't need to worry about provisioning and configuring the nodes and then installing the network components on it. This is handled by the managed solution, as is the communication between the different nodes which make up the blockchain network. All you may need to do is specify at a high level what form of communication is required. Additionally, the managed solutions will also issue identities to the different users, and the specific permissions for these users can be assigned through their portal rather than by editing some config files. These cloud services may also include a standard user interface in order to interact with a deployed smart contract. Though this may not be the solution which you have in a production setting, this can often be ideal in order to test out your solution in the development or testing phases. Of course, these cloud services will include other features such as auto-scaling of the VMs which make up the network and also monitoring services which you can count on. But the big picture view is that the users of these managed blockchain solutions can just focus on the development of applications and smart contracts. In the previous video, we covered the reasons why it makes sense for many organizations to make use of one of the managed blockchain services available on cloud services such as Azure and AWS. We will now take a closer look at the Azure Blockchain Workbench, which is the managed blockchain solution offered by Microsoft's Azure. The principle behind the Azure Blockchain Workbench is for users to be able to configure and then deploy a blockchain-based application with just a few clicks. So if you were to consider why exactly you might use the Azure Blockchain Service, well, this is where you only want to be tasked with the responsibility of building your blockchain-based application, and the implementation of the blockchain network itself is something which you wish to be handled by a service. The existence of an underlying blockchain network will be entirely transparent to the users of the application, and in fact, most of the details will be transparent to the developer of the application itself. We can now take a closer look at some of the properties of the Azure Blockchain Workbench. So this is a service which is available as a solution in the Microsoft Azure Marketplace. The Workbench deploys a blockchain network using a number of the different Azure services. For example, there will be VMs which will be provisioned, as well as databases which will be used in order to store the state of the network and also the contract data. Even as a developer of the blockchain applications, you need not be aware of all of these details, but it will help for you to understand exactly how the network is set up. When using the Workbench, you can manage the identities for the different participants in your network by means of the Azure Active Directory. So you need not concern yourself with managing certificate authorities, issuing certificates, and so on. All you need to make sure is that anyone who wishes to connect to your network or application has an Azure Active Directory account, and then using the application's interface, you can allow them access to your app. In addition, the Azure Blockchain Workbench uses a modified version of Ethereum in order to implement the blockchain network. The way it gets around many of the shortcomings of Ethereum is by making use of proof of authority algorithm for consensus instead of the proof of work consensus mechanism. The proof of work algorithm is suited for an environment where there are many untrusted nodes you need to work with. In the case of the Azure Blockchain Workbench, however, it is a private network, so the proof of authority consensus mechanism will suffice. Another feature of the Azure Blockchain Workbench is that it includes a user interface which allows you to upload the smart contracts which you have developed and then deploy it to the blockchain network. And then following that, you can continue using the user interface in order to interact with that deployed contract and invoke transactions which are recorded on the blockchain. We can now zoom in on some of these properties, starting with the different Azure services which are used by the Blockchain Workbench service. One of these, as I touched upon, includes a SQL database, which will be used to store the state of the blockchain network. Some additional network-related data will be stored using an Azure storage account. There will also be VMs, which will be provisioned and will allow interactions with the various components of the blockchain network. And these VMs will also be configured to scale according to the traffic on your applications. A network resource group will also be set up, and this will include a load balancer and also a public IP address, which can be used in order to access the Azure Blockchain Workbench web app. Moving along now to the Azure Active Directory service. This is the one which allows users to log on to your blockchain-based application using their corporate IDs. Not only that, you also have some fine-grained control over what degree of access the user has to the application. And this is something which you can define in the application configuration file. That is something we will take a closer look at in just a little bit. Moving along now to the consensus mechanism which is used for the underlying blockchain network. And as discussed, this is the proof of authority algorithm. The principle behind this is very simple. Any user who has been explicitly granted authority will have the power to invoke transactions on your application. So the only check which needs to be performed is whether a user has the permissions to invoke the transaction, and this makes the blockchain network itself very computationally efficient and allows it to generate the throughput which is required for an enterprise-grade blockchain solution. The proof of authority mechanism also means that there is no mining involved in the blockchain network, and this is a big modification which has been made to the Ethereum source code in this Azure implementation. Moving along now to the user interface which is provided in the service. As I had mentioned, you can use the UI in order to upload the contracts which you have developed along with the configuration file which goes with it, and then you can deploy your contract to the network from the UI itself. In fact, you can continue using this UI in order to interact with the deployed contracts and invoke transactions. It is also possible for you to define exactly what will be visible in the UI by means of a configuration file. So just to sum up, the purpose of the Azure Blockchain Workbench is to allow developers to focus on the task of building a blockchain application. The implementation of the blockchain network itself and the maintenance of all of the services which are required for it is something which will be handled by Azure. So the question to ask at this point is, what exactly constitutes an application on the Azure Blockchain Workbench? Since this is the part which a developer will need to focus on when making use of this service. Well, there are specifically two files which an application developer will need to construct. The first of these is a smart contract, and this is very much the same as a Solidity smart contract which is written for Ethereum. The second file which a developer will need to build is something known as the configuration file. The contents of this configuration file are tightly coupled to the contents of the associated smart contract. However, it includes some additional details which have to do with roles and workflows associated with your application. Let us now take a closer look at each of these files, starting with the smart contract. The Azure Blockchain Workbench uses Ethereum under the hood, and while this is a significantly modified version of Ethereum which uses a different consensus mechanism, what has not changed is the support for smart contracts which are coded in the Solidity programming language. In case this is a language you're not familiar with, it is an object-oriented language. So if you have any prior experience using C++, Java, Python, or any such language, Solidity should come rather easily to you. However, this is a domain-specific language, and you are unlikely to find any use for this language outside of Ethereum. This is because, unlike general-purpose languages, Solidity has rather limited types and features as well. For example, though you do have strings in the language, there is no native support as of this recording for any string manipulation operations. This is because string manipulation is something which should not be handled by smart contracts and should instead be handled by a client application which is connecting to the contract. The smart contract should be used in order to define the transactions which you would like to record onto the blockchain network, along with the functions which will be used to view the contents of the network. So with the smart contract, we have completed one portion of the definition of the blockchain application, which we can deploy to the Azure Blockchain Workbench. In the next video, we will take a closer look at the accompanying configuration file. In the previous video, we covered the fact that to define an app for the Azure Blockchain Workbench, there are two files which we will need to define. The first of these is a smart contract, which is coded in the Solidity programming language. Which takes us along now to the second file, which is the config file. This is a file which is written in the JSON format, and this essentially serves as metadata for the blockchain application. It is through this metadata that you will define the roles and workflows for your app. The roles will be configured for the different users of your application, and this is where you can define, for example, who has access to perform which operation in your underlying contract. In fact, you can ensure that the operations defined in your underlying contract are executed in a certain order by means of a workflow definition. For example, if the application involves recording transactions related to the purchase of products, and each purchase needs to be signed off by someone in the management in your organization, this logic can be coded by means of a workflow in this configuration file for your blockchain workbench app. So we have now discussed at a high level that this config file includes the definition of roles and workflows. We can now get deeper into these topics by first taking a look at what exactly constitutes a role in the context of the Azure Blockchain Workbench. Well, when you're defining a role in this configuration file, all you need to specify are the name of the role and optionally an associated description. Once you have defined such a role though, this will be assigned explicitly to participants in your application, and then these participants are identified by means of their Azure Active Directory accounts. So once you have mapped an Active Directory account to a particular role name in the context of your application, you will need to apply these roles to specific steps in your workflow. So these roles end up determining who has the ability to invoke specific steps in the workflows. And what are workflows? Well, one simple definition is that it is effectively a collection of states and actions, where the performance of a particular action causes the application to move from one state to another. While this seems consistent with the generic definition of a workflow, to understand exactly what it means in the specific context of an Azure Blockchain Workbench app, we can now take a look at some of the fields which you need to define within a workflow. We start off with a name for the workflow, and this needs to match the name of the associated smart contract. In addition, you may also include a display name and a description for the workflow, and these are followed by some of the more meaningful fields, starting with the properties fields. Each property which is defined within a workflow definition needs to map to a property in the underlying smart contract. In fact, the name of the property will need to match the name of the field in the contract. In fact, the same thing also applies to the functions defined within a workflow, which map to the functions defined in the smart contract. So you can now clearly see that there is a very tight coupling between the workflow definition and the associated smart contract for the app. The reason the functions and the properties are included in the workflow definition is to allow the invocation of the function and the ability to view the values of the fields in the underlying contract using the blockchain Workbench UI. Other details included within the workflow definition are the initiators of the workflow, and this maps to certain roles which have the ability to create these workflow instances. You will recall that the roles themselves map to specific Azure Active Directory users. The other details included within workflows are the different states which make up the workflow, and we will soon see that you can also define the conditions under which you can transition from one state to another. A workflow will also need to include a start state, and this represents the state of your workflow once it has been initialized. The initialization itself will happen through the constructor, which is what you will define in the underlying smart contract, and there will be a corresponding entry for that constructor within this workflow definition. We can now take a closer look at some of these fields, starting with the workflow states. For each state which you define within the workflow, it will include a name for the state, also whether this particular state represents a success or a failure, and optionally, there is a %complete field which you can specify in order to portray at what stage of the entire workflow process this current state represents. Within a state definition, you can also define a collection of transitions which determine the state to which this workflow can move to following this current one. So what exactly are included within the workflow transition definitions? There is a field called allowed roles, which lists the roles defined within the scope of the application, which can initiate a particular transition. So these allowed roles will be one of the roles defined within the configuration file. There is another field called allowed instance roles, and this will map to roles which are defined as fields in the underlying smart contract. Each of these allowed instance roles maps to an address variable within the contract state. So while the allowed roles map to application level roles, which in turn map to Active Directory users, these allowed instance roles map to specific account addresses defined within the underlying contract. These two fields, though, have the effect of determining who is allowed to initiate a particular workflow transition. To specify exactly what happens during a transition, you will need to map this transition to a function in the underlying contract. This can, for example, invoke a transaction which will be recorded on the blockchain. Another detail included in a transition is a list of next states. So to summarize, a particular transition definition in a workflow, who gets to initiate the transition, the specific function which will be called when that transition is invoked, and also what the next state will be once that transition is performed. So now that we have gone into the details of the workflow definition, we can zoom back out a little bit and then take a look at what exactly makes up an Azure Blockchain Workbench application. And the answer is that it includes two files. One of these is a smart contract written in the Solidity language, and the other is an accompanying configuration file. And this config file includes definitions of roles and workflows and is in fact tightly coupled to the smart contract. So with these two files, our application will be defined, and then we zoom back out. We see the purpose of the Azure Blockchain Workbench. To build a blockchain application, all we need to do is to specify two files, and the entire implementation of the blockchain network is something which will be handled by the blockchain Workbench service. In the previous videos, we took a look at the managed blockchain solution, which is available on Microsoft's Azure service. We will now take a look at the managed blockchain offering on Amazon's Web Services, which is known as Amazon Managed Blockchain. So one thing to keep in mind is that Amazon Managed Blockchain is not the only cloud-based blockchain solution which is offered on AWS. In fact, there are a handful of pre-built solutions which this cloud service offers, and you are free to choose the one which suits your specific use case. To summarize, the blockchain solutions which are available include AWS Blockchain Templates, and this is the one where you can build a bare bones blockchain network. There is one known as Quantum Ledger Database, and this is especially helpful if you'd like to access a blockchain network as though it were a SQL database. And finally, there is the Managed Blockchain service, which is Amazon Managed Blockchain. And this is the one we will be exploring in greater depth during this course. We can now take a somewhat closer look at each of these offerings, starting with AWS Blockchain Templates. This is the one you will use if your requirement is simply to set up a basic blockchain network. And this is one which will allow you to keep control of many of the configurations for the network. This particular service makes use of AWS CloudFormation in order to define and then deploy the various components which make up your blockchain network. In case you haven't used this particular service, CloudFormation effectively allows you to define infrastructure as code. That is, you can define all of the infrastructure which you require within a JSON file, and then that infrastructure can be provisioned by simply passing along that file over to CloudFormation. As of this recording, AWS Blockchain Templates allow you to provision an Ethereum network as well as a Hyperledger Fabric network. One thing to keep in mind is that even though this will help you set up the network, a lot of the configuration details are left to the user. And while this gives you a greater degree of control over the network, it does come at the cost of some convenience. Moving along now to AWS's other offering for blockchain solutions, and this is the Amazon Quantum Ledger Database. This is specifically meant for those who have prior experience using an RDBMS and like the interface which is used to communicate with such a database, but also at the same time want the security of a blockchain. So this particular service will have an immutable transaction ledger, and this is where all of the transaction information can be recorded just as you would in a regular blockchain. The difference with this particular ledger implementation is that accessing the data can be done by means of a SQL-like API. That is, you can run SQL-like queries in order to retrieve the data and also perform analysis on that data if required. A benefit of this particular blockchain solution is that it has the ability to scale automatically depending on the demand for the service. Moving along now to the Amazon Managed Blockchain solution. Like the others, this also sets up a blockchain network, but also does a whole lot more to ease the burden of setting up and managing such a network. For example, AWS will handle all of the identities for you, so you can identify participants in your network just by means of their AWS accounts rather than having to issue certificates and manage them. Once you have set up your blockchain network, it is possible for you to invite new members to join in, and this invitation can be extended to another AWS account, and you can also configure some kind of voting policy for all of the existing members of your blockchain network to decide whether this new member should be invited. And much like the Quantum Ledger database, this particular service also ensures that the instances scale according to the demand which is placed on it. Moving along to some of the other properties of this service, Once you have set up your blockchain network, it is possible for you to download and install the smart contracts from a Git repo. This could, for example, allow you to automate the deployment process for smart contracts. One thing to keep in mind, though, is that in spite of a lot of the details of setting up and managing the blockchain network being abstracted from the user, there is still a lot of manual setup required at the time of this recording in June of 2019. This is likely to change in the near future, however, since all of the blockchain solutions are constantly in a state of development. Also, at the time of this recording, the Amazon Managed Blockchain Service is only available to set up a Hyperledger Fabric network. However, a solution based on the Ethereum network is currently under development, and it is possible that by the time you view this video, that will be ready as well. So these are some of the high-level properties of the Amazon Managed Blockchain Service. We can now dig down a little deeper into the specific details which we will need to implement on our own. For one, when we are setting up the network, it is possible for us to create one which includes just a single organization or spans multiple organizations. The requirement, though, is that all of the organizations involved must have an AWS account. In the case of the Hyperledger Fabric network, the network which is provisioned will include an ordering service as well as the certificate authorities for the different organizations. Once you have set up a basic network, you can invite other members to join the network, and it is also possible for you to remove an existing members from the network. However, any invitation for new members and revocation of existing membership needs to go through a process. This is where a proposal is first issued containing the invitation or revocation details, and typically, at least some of the existing members of the network will need to approve this proposal. This approval process takes place by means of a vote, and it is possible for you to define a voting policy. For example, whether an approval requires a simple majority or a specific threshold of the existing members. One more thing to keep in mind is that any proposal will also have an attached expiration date. This could range from a minimum of 1 hour to a maximum of 1 week. So any proposal to invite a new member or remove an existing member is subject to a vote, and this vote does have an expiration date. So all of these are great features which are offered by the Amazon Managed Blockchain Service and does greatly simplify the task of setting up and managing a blockchain network. However, in order to interact with the blockchain network, which includes the deployment of smart contracts and interactions with them, you will need to set up a client. At the time of this recording, this client setup requires several installations and configurations. For example, you will need to set up Docker and then run a Docker container for a Hyperledger Fabric CLI. It is this CLI which you can use in order to interact with the network. In addition, you will need to make use of some configuration files in order to define the channels which make up your network. This is in the case of Hyperledger Fabric. And you will also need to make use of the CLI in order to install and then instantiate chain code or smart contracts. So when using the Amazon Managed Blockchain Service, you should be aware that though this abstracts away a lot of the implementation details from the user, it still requires considerable user involvement in order to set up the network and also deploy smart contracts. In this exercise, you will start off by summarizing the two files which make up an application on the Azure Blockchain Workbench. During the course, we cover the fact that such an application consists of two files which are tightly linked to each other. You will need to recollect exactly what these files are and what they contain. Next, you will describe the three different blockchain services offered on AWS which were covered during this course. In addition to identifying each of these three services, you will also need to recall exactly what purpose they serve. Both of these topics were covered during this course, So please pause this video and then spend some time to perform these tasks on your own. For the first task in the exercise, you needed to summarize the two files which make up an application on the Azure Blockchain Workbench. The first of these files is a smart contract, and this is one which is written in the Solidity programming language. It is within this files where you will define the different queries and also the transactions for your blockchain application. With just a smart contract though, this application won't be much different from a standard Ethereum application. The detail which sets apart an app for the Azure Blockchain Workbench from a regular Ethereum application though is the configuration file which goes along with the smart contract. This is a file which is defined in the JSON format, and it includes definitions for roles and workflows for the application. This config file is tightly coupled to the smart contract, and there are several properties which map directly to the functions and fields defined within the underlying contract. The config file also includes workflow definitions, and within the workflows themselves, you'll have a number of states. There will also be several actions which map to functions in the underlying contract, and it is the invocation of these actions from each of the states which will initiate transitions. The definitions for these are included within the config file. For the next task, you needed to describe each of the three AWS blockchain services which were discussed during this course. One of these services is called AWS Blockchain Templates. Now, this is the most basic of these services, and all it does is set up a simple blockchain network. The configuration of the network, the deployment and management of smart contracts is entirely up to you. At the time of this recording, the AWS blockchain templates are available to set up both a Hyperledger Fabric network and establish an Ethereum network. Another blockchain related service on offer on Amazon's Web Services is the Quantum Ledger database. This is targeted at individuals who would like the convenience of using a relational database, but with the added security of recording their transactions on a blockchain. This is achieved by including a SQL-like interface in order to access and also analyze the data which is stored on the blockchain. So while we briefly touched upon the topics of the AWS blockchain templates and the Quantum Ledger database, we looked in more detail at the other blockchain service, which is the Amazon Managed Blockchain. Now, this is a fully managed blockchain service offered by AWS, and as of this recording, can set up a Hyperledger Fabric network on our behalf. Once this network has been provisioned, it is possible for us to invite additional members to join the network, and if needed, we can also remove existing members from the network. Extending invitations and proposing the removal of members, though, is subject to a vote. In this demo, we will be setting up a Hyperledger Fabric network using AWS Managed Blockchain. For this, you will require an AWS account, and this course assumes that you already have such an account or will be able to create one on your own. Once you have the account, you can log into the AWS Management Console, and it is from this point where we begin this demo. Before we can begin using the AWS Managed Blockchain service, there are a few prerequisites which need to be met, and this is what we will get started with right now. So from the Management Console, just make note of the user you are logged in as, which in my case is cloud.user. And the region I'm now connected to is North Virginia. At the time of this recording in May 2019, AWS Managed Blockchain is still a very new service, and AWS typically launches its new services in the North Virginia region. By the time you view this, there may be other regions in which this service is available, in which case you should pick the region which is closest to you. But for me, I'm just going to stick with North Virginia because that is the only choice I have. Now, setting up the prerequisites will require us to access some of the other AWS services, So we can head over to the services section, and then from there navigate to the IAM console. IAM is short for Identity and Access Management, and this is where we will need to provision a new user, which will be the main user of this blockchain network which we are about to set up. When creating a new user, we will be able to specify the permissions which need to be attached to it, and a collection of permissions will belong to a policy. We will first head over to the console, and we will now create a new policy, which I repeat is a collection of specific permissions on AWS resources. So from the policy section, you will see that there are a number of different pre-built policies already available in Amazon Web Services, but we will need to create a custom policy of our own. So we head over to the Create Policy button, and then from here, we will need to fill in the details of the policy we are about to create. Using this visual editor, we will be able to select a particular service for which we wish to assign permissions, and then we can define those permissions on the service. Alternatively, we can also specify the permissions as a JSON structure. This is what we will be doing now. So we head over to the JSON tab, and the policy JSON which we will be creating will be rather simple. Specifically, we want the user which we are about to create to have the ability to create VPC endpoints. So this is the JSON which we need to define for that. And just in case this JSON definition changes over time, you should be able to find the latest version at the URL on the screen in front of you. And the reason we would like the user managing the blockchain service to be able to create VPC endpoints is because we will need such an endpoint in order for users to connect to the blockchain network. You can view from the asterisk symbols in this definition that this particular rule makes use of that wildcard, and there will be several different actions and resources to which this will apply. To get an idea of the specific actions, we can head back to the Visual Editor tab. And in this view, we will be able to see that this applies to the EC2 service, and that there are 18 different actions which are included within this policy. If you'd like to get an idea of what these actions are, you can click on this, which will expand the view, and then expand the Actions menu. We can see over here that the permissions which are included within the policy include 6 different list permissions and 12 different write permissions. You can click on each of those to view the specific permissions, but I'm just going to close out of this. We can see here that this particular policy applies to all of the resources, and we can also set the conditions under which these rules apply. For instance, we can configure multi-factor authentication and also specify that only requests coming in from specific source IPs will be able to get the permissions associated with this policy. Now I'm not going to enable any of these, and we'll just close out of it. We can now head back to the JSON tab and then click on Review Policy, which will be a final step towards creating this. So we can name this policy Creating and Managing VPC Endpoints. You may specify a description if you wish, but finally you can just confirm that this policy does what you want it to, and then click Create. With our policy in place, it is now time for us to create a new user to whom we can attach this policy. So heading over to the Users menu, we'll go ahead and click Add User. Now, this particular user will represent the first organization in our Fabric network. So I'm going to call this org1. Note here in this demo that we will start off by having a single organization on the Fabric network, and later on in the learning path, we will add a second organization. In any case though, this particular user will represent the first org. Following that, we enable programmatic access, which means that an access key ID and a secret access key will be generated, and those will be supplied as credentials when connecting to the network as this org1 user. So with that done, we move along to the next step. And this is where we can attach the policy which we created previously to this user. But it's not just the permissions associated with our custom policy which we will need to attach. since this user does require a few more permissions. When we click on Attach Existing Policies directly, we will first attach our custom policy, which you will recall was called Creating and Managing VPC Endpoints. And you will likely need to search for this particular policy in the search bar. Once you find it, you can select this policy. And then following that, we will need to attach another policy to this user. And this is to be able to have all access related to AWS Managed Blockchain. So we can search for managed in this search bar. And the one we are looking for should be the first result which is returned. Just to confirm, we can expand this particular policy. And this one is called Amazon Managed Blockchain Console Full Access. This is one thing which we do require. So we can go ahead and select this policy. And then if we wish to give more permissions to this user, we can expand the next policy, which should be Amazon Managed Blockchain Full Access. So in addition to the console, we should also be able to manage the blockchain from the CLI, for example. So I'm just going to go ahead and select this policy as well. There is another policy which I'm now going to attach to this user, and this is related to Amazon's S3 service. Amazon S3 is AWS's storage service, and this is where some of the certificates which our users will require will be stored, and we want to be able to download them to our Fabric network nodes. And for this purpose, I'm going to assign S3 access to our organization's admin user. So in this case, I'm going to give the most liberal policy, which is Amazon S3 full access. So with these policies selected, we have all the permissions which this user needs. So we can proceed over to the next step, where we can add tags for this particular user. Now this is purely optional, so I'm just going to skip this step and then move on to the last step of the process. And this is where we just need to review all of the permissions which we have assigned to the user. Once everything looks good, we can just go ahead and click Create User. And with that done, this new user has been created, and we have been assigned the access key ID and the secret access key, which we can use together in order to access AWS programmatically or using the CLI. One thing to keep in mind is that this secret access key will only be accessible right now. So you do need to copy it over and store it somewhere safe. Or alternatively, you can download it, both the access key ID and the secret access key, in a CSV file by hitting this button. And with that done, we have now successfully created the admin user for our blockchain network. So far, we have created the admin user for the first organization in our Hyperledger Fabric network. This admin user has been given all of the permissions necessary in order to create and then manage the blockchain network. And these include access to the AWS Managed Blockchain Service, also the permission to create a VPC endpoint, and access to AWS's S3 service, from which certificates will be downloaded later on. Now, when we do create a blockchain network, it will be provisioned on an AWS EC2 instance. EC2 being the service which will allow you to create VMs on AWS. In order to enable connections to our Hyperledger Fabric network from both within the network and also from our own machines, we will now need to configure a security group, for which we navigate to Services and then select the EC2 service. From the EC2 dashboard, we navigate along the menu on the left to the Network and Security section, and then select Security Groups. So just in case you're not aware, a security group in AWS can be thought of as a collection of firewall rules. So these will include a number of inbound and outbound connection rules, and you can attach a security group to a VM instance so that all of those rules will apply to that instance. So in our case, we will need to create such a security group. So when we click this button, we will go ahead and first give a name to this, which I'm going to call HF client and endpoint. HF here being short for Hyperledger Fabric. You may specify a description, and I'm now just going to state that this will permit traffic between our Hyperledger Fabric network and the internet. And we can also say which VPC or virtual private cloud this security group should belong to. A VPC in the AWS world can be thought of as a virtual network. While it is possible for you to set up this blockchain network on your own VPC, I'm going to use the default VPC which was provisioned by AWS. So with that, I'm just going to go ahead and hit create. And this HF client and endpoint security group has been provisioned. Now, as I mentioned, a security group is a collection of inbound and outbound traffic rules. And at the moment, this group does not have any of those. So in order to select this group, I'll first unselect the other security group, which is the default one, which was provisioned. And then with this security group, we can configure the rules by going over to the menu at the bottom and then clicking on the inbound tab, where we can set up the inbound rules for this security group. Now I'm going to copy over the ID of this new security group because we will be using it shortly. And then we can edit the inbound rules by hitting the edit button. Now, just to summarize, when we attach this security group to a VM instance, the connections which are allowed to come into that instance will be governed by the inbound rules we can set up here. So for example, if you wish to permit all kinds of traffic from any VM which has this security group assigned, then we can first go to the type column, and then from the types of connections we select all traffic. And following that, we leave the protocol and port range as they are because we want this inbound rule to apply to all types of traffic using all protocols and across any of the ports. But we specify that this incoming rule only applies to those instances which have this same security group attached. So for example, if we want two instances to be able to communicate freely with each other, we just need to attach the same security group to both of them. So this will apply to all of the instances which we will add to our AWS managed blockchain network. So with that done, we need to attach one more inbound rule, and this is to enable connection via SSH from our own machines to the instances in this managed blockchain network. For this, we will need to be a little more specific in our inbound connection rules. So for the type of traffic, we select SSH, the protocol will be set to TCP, and the port range will be 22. So this rule means that only SSH connections coming into port 22 will be permitted, and we can also specify the source from which these connections will be allowed. So to permit SSH connections from our own machines, we can expand this dropdown and select My IP. And you will automatically see your own IP address populated in this field. So just to summarize, we have added two inbound connection rules to the security group, and the security group will be applied later on to all of the instances on our blockchain network. The first of these rules permits all connections between the instances which have the security group attached, that is, all instances on our blockchain network. And the second one is to enable SSH connections from our own machines to the instances on the blockchain network. So with that, we can hit save, and our inbound rules have been saved. And then we can take a look at the outbound rules for this security group, clicking on the outbound tab. And you can see that by default, there is no restriction on outbound traffic from within this security group. So with that done, we are satisfied with the outbound rules as well as the inbound rules which we just configured. And the setting up of our security group is complete. It is now time for us to set up the instance or the VM which will host all of the Docker containers which will make up our Hyperledger Fabric network. This is what we will do in the next video. We have now set up a security group which will enable all communications between instances on our Hyperledger Fabric network, to which we will need to attach that security group. We have also permitted access from our own IP addresses to the network. So it's now time for us to set up an instance on which the network can be provisioned. To do that, we navigate in the menu on the left over to Instances, and then from there, we will go ahead and click on Launch Instance. The first thing we need to do when creating a VM instance is to choose an Amazon machine image. This machine image will include an operating system, maybe an application server, and a few pre-configured tools out of which the VM will be provisioned. Now, if you happen to be setting up a Fabric network in a production setting, you may wish to choose a large VM, but for the purposes of this demo, we really don't need anything too fancy and will stick with the free tier Amazon Linux 2 AMI. With our image selection complete, we will need to choose an instance type, and once again, we don't need anything too fancy, and I'm going to stick with the t2.micro instance, which is still in the Amazon free tier. The next thing for us is to configure some of the details for this instance. Firstly, I'm just going to leave this as one instance to be created for now. And this is the point where you can specify the VPC in which this will be provisioned. So I'm now going to leave this as the default network, which is the only one I have currently. And do make sure if you're using a custom VPC that you provision this instance in the same VPC to which the security group we created previously has been attached. The next step for us is to select the subnet within this VPC. And for the purposes of this demo, this is not particularly important. So I'm now just going to say that I have no preference. Next, we will need to state whether we would like this VM instance to have a public IP. And I'm going to use the default subnet setting so that a public IP will be provisioned. A public IP will be required in order for us to be able to connect to this VM instance from our own machines. So with this configuration complete, we move ahead to the next tab, which is to add storage. And I'm going to leave this as the default, where an 8 gig hard drive will be attached to the instance. Moving ahead to the next tab. Once again, you can choose to add tags to the VM instance, but I'm not going to do any of those. And then we'll need to configure the security group for this instance. This is where we will attach the security group we have already created, which is called HF Client and Endpoint. So while there is an option to create a new security group at this point, we just need to choose the option to select an existing one. And this is where we will select the one we just created. And with that, we'll just have to review this instance creation details. So we are creating a T2 micro instance type out of the Amazon Linux 2 AMI. We can view the security group as well as the rules which are attached to it. And you can review all of the other details as well. And once you're satisfied, you can just hit launch. So the instance provisioning is not yet complete because we need to now specify a key pair which can be used in order to connect to this instance. So at this point, we can use an existing key pair if there is one already. But because I don't have one, I'm going to choose the option to create a new key pair. This one I'm going to call org1-key. And then following that, click on the button to download the key pair. With that done, the key pair has been downloaded as org1-key.pem, and keep it in a safe location because we will be using that to access the VM later on. And at this point, we can just go ahead and hit launch because all of the details for this instance creation have been specified. And this provisioning of the instance should take a few seconds or maybe even a minute or two, but I'm going to fast forward this until we get this notification that the instances are now in the process of being launched. We can choose to view the instances, and in my case, this instance is still provisioning, so I'll once again fast forward, and the instance is now in a running state. We can select this instance and then check out all of the details associated with this in the frame in the bottom of the page. For example, we can review the security group as well as the inbound and outbound rules of that group. But now that our VM instance is ready, we have fulfilled all of the prerequisites in order to set up a Hyperledger Fabric network using the AWS Managed Blockchain service. In the next video, we will use that service and then provision the network for this single organization, which will run as Docker containers on this VM instance we have just created. We are now ready to begin setting up a Hyperledger Fabric network using the AWS Managed Blockchain service. Let us quickly summarize what we have done so far as the prerequisites are concerned. We first set up a user who will serve as the administrator for the blockchain network. And for this user, we created a policy which includes permissions to create a VPC endpoint. We will be setting up such an endpoint when we provision the network. We also set up a VM instance which will host all of the containers which will make up our one organization Hyperledger Fabric network. To allow this network to scale beyond the single instance, we need to be able to allow those instances to communicate with each other, for which we set up a security group which not only allows unrestricted communication between instances connected to that group, but also permits connections from our own machines via SSH. With that done, we will now head over to the services menu and then over to the Amazon Managed Blockchain service. So just to summarize the purpose for this service, there are several steps involved when setting up a Hyperledger Fabric network, and this includes details such as setting up identities, provisioning hosts, and everything. Essentially, there is a lot of scaffolding work. With the Managed Blockchain service on AWS, all of that is abstracted from the user, and you can mainly focus on the development of smart contracts and applications for your blockchain network. So let us now proceed with setting up a Fabric network using this service. So if you'd like to view the pricing for the service, this is a section where the details are available. And some of the high-level steps as far as setting up the network are concerned are listed here. So initially, we will set up the network for just a single organization, but later in this learning path, we will add another org to our network. So there are other details available in this page. So there are some benefits and features of the AWS blockchain service, as well as a few sample use cases which you can take a look at. But what we're really interested in, though, is to create a blockchain network, for which we just click this Create Network button. You'll instantly see that there is only one option available, as of this recording at least, to set up this network. And specifically, we can only set up a Hyperledger Fabric network. It is quite possible that by the time you view this video, there will be support for an Ethereum network as well. For the purposes of this demo, though, I will stick with the only option which I currently have, which is Fabric. And then there are also two options available for a Fabric network. You could use a starter network or a standard network. And to view the differences, you can click on this additional info button. But just to summarize the differences, a starter network is smaller and includes fewer features than a standard network. For the purposes of this demo, a starter network is more than sufficient. Moving along now to the details of the network which we wish to create, we specify a name. So in my case, I'm going to call this Fabric-Network. And then beyond that, we can also configure a voting policy. The voting policy is what determines who gets to become a member of this Fabric network. So by default, there is a simple majority which is required among the existing members in order to vote in a new member. We will cover later on in this learning path, when adding a new member, that a proposal is initiated, and following that, this voting policy must be satisfied within a specific time period. We can change this from a simple majority to a minimum percentage of the existing members who need to provide an approval. And this approval is also time bound, which is set to 24 hours by default. But at the time of this recording, this can be set to a value up to 168 hours, which is 1 week. So with our network name and the voting policy set, we can click Next. And then from here, we'll need to create a new member of the Fabric network. Since this member belongs to the first and only organization for now, we can call this org-1. And then scrolling further down, we can specify the name of the admin user for the certificate authority for this organization. So I'm going to call this org1 admin. And then I'm going to use the same string for the password as well. To view the password, you can click this Show Password checkbox. And once this admin user credentials have been set, we are now ready to proceed to the next step since we have added a member to our network. So the last step here is to review all of the details. This includes the name, the voting policy, and the details of the first member of our network. And if everything looks good, we just click Create Network and Member. This will set up the AWS Managed Blockchain Network configuration, and this will take several minutes to complete. But while this is going on, we can view the details of our network, which are yet to be populated. From the Details tab, we can switch over to the Members tab, which will show us the different members who are part of this network. And this is also the menu from which you can create new proposals. That is, you can invite other AWS accounts to join the Fabric network. These accounts could belong to your own organization or to an external one. Scrolling further down, there is a section called Members Owned by You, and these are the members which belong to your AWS account. It is possible for you to have multiple members from the same AWS account as part of this blockchain network. Moving along now to the proposal section. This is another section where you can propose addition of new members to the blockchain network, and you can also propose the removal of an existing member. If a proposal has been made by either you or by someone else within the blockchain network, then those active proposals will show up in this section, and this is where you can issue your approval or denial of that proposal. And once you have supplied an approval, then those proposals will show up in this completed section. Heading back now to the Members tab, you will observe that this org1 member is still being created. So this may take a few minutes. And then when we click on that org1, we view the details of the organization member. And we can also take a look at the peer nodes which belong to that member. As of now, there are no peer nodes, and we will need to set that up on the VM instance which we had provisioned a little earlier. As for now though, we will scroll up here and then head to the network section within the Managed Blockchain Service. And for me, this Fabric network is still in the status of being provisioned, but I'm now going to fast forward until its status reflects that it is available. Scrolling further right, you can confirm that the Hyperledger framework which is in use is Hyperledger Fabric version 1.2. Now, when we click on this Fabric network, we can view the details, and this has much more information than it did previously, since this network definition is now ready. This includes an ordering service endpoint as well as the VPC endpoint service name. However, there are a few more steps which we need to go through before the network is ready for use. And the first thing we'll do now is to create a VPC endpoint. So by clicking this button, we specify the VPC to which this will be attached, which in my case is the default VPC. I'm going to select one of the subnets from there. And then following that, we will need to specify a security group which will be attached to this VPC endpoint. So this is the one which we have created previously. Once that selection is made, we can go ahead and click Create because the VPC endpoint service name was already set when we created the network. And with that, a VPC endpoint has been generated. It is this VPC endpoint which will be used in order to connect to this blockchain network. At this point, we head over to the Members tab, and then clicking on org1, we can take a look at its details, including this org's status, and this is also now available. In the previous video, we created an instance of a blockchain network using the AWS Managed Blockchain Service. While this has performed a lot of the network configurations, it is far from complete. We haven't quite set up any of the peers in our network yet, and we will now need to connect to the VM instance which we set up earlier, and will install a number of different tools so that it can function as a Fabric client. So the AWS Managed Blockchain Service, at least as of this recording, still requires us to do a lot of work, but it handles all of the identity creation and the network setup for us, and also provides an interface in order for us to manage membership of the network. It is now time for us to set up the VM instance. So for that, we head over to the Services menu, and then under the Compute section, over to the EC2 service. From here, the instance which we created previously will be accessible from this Running Instances view. And then here, we can see that this instance is currently in the running state. Now to connect to it, all of the details which we require will be available when we hit this Connect button. And this shows us what we need to do in order to connect to this instance using SSH, which we will do so from our own machines. To do this, we will need to make use of the key pair which we generated previously when provisioning the VM. Specifically, we will make use of the private key, and we need to ensure that the user we are running as has read permissions on that private key. So to do that, we will need to run this command from our command line, and I'm bringing up the shell on my machine, which is a macOS terminal, and you can bring up any of the shells on your own machine for this. You will, however, need to navigate to the location where the private key file was downloaded, which in my case is this downloads directory within my home folder. I'll just do an ls to view what files are visible here. In my case, there is this credentials.csv file, which includes the access key ID and the AWS secret access key for the user which we provisioned earlier on in this course. There is this key pair which was generated when we provisioned the VM instance, and the private key can be found in this org1-key.pem. To set read permissions on this, I'm going to run chmod 400 on this file, and then following that, the instructions to use that key in order to connect to our VM instance can be found in the AWS page. So this is the specific SSH command which we will need to execute. So I'm now going to copy that over and then execute it from my shell. So just to summarize, we are using the key pair which we generated earlier on in order to connect to the VM instance. Since we are connecting to this machine for the first time, there may be a warning which is issued. We can just say that it is safe to connect to this host and hit enter. And now the connection to that EC2 instance has been successfully established. Now this is the host on which we will be setting up all of the different components of the Hyperledger Fabric network. Each of these components will run as Docker containers, but before we do that, there are a few prerequisite tools which we will need to install. I'll go ahead and clear the screen, and then first of all, we will need to run a yum update. This will update all of the system software and their dependencies, and this may be required because all of the tools which are included as part of the Amazon Machine Image or AMI may be a little out of date. So running this could take a while. So I'll just fast forward. And it is likely that a number of different tools will be getting updated in this process. But once it is complete, we can move along to the next step. And this is where you will need to install the Telnet tool. So you can use yum to do this, and the command is sudo yum install telnet, and you can specify the -y flag so that all of the prompts which will come up will be automatically answered with a yes. Once Telnet is installed, we need to install one more tool, and this is Emacs. So I'll go ahead with this installation and fast forward. And once Emacs is ready, there is another crucial tool which we need to install, and this is Docker. Since each of the components which make up the Fabric network will be running as Docker containers, this is a tool which we do need. So once again, we use yum to install this. And once Docker has been installed, we will need to start the Docker daemon. And the way to do that is to run the command sudo service docker start. Once we execute this, the Docker service, that is the Docker container engine, will be up and running. Now, to be able to run Docker commands without having to specify sudo each time, we will need to add this ec2-user, which is the default user for this instance, to the Docker group. We do that using this usermod command. And with the Docker setup complete, the next step for us is to install Docker Compose. Docker Compose, in case you're not familiar with it, is a tool which enables you to run multi-container Docker applications. So you can specify the entire application within a single YAML file. And this is exactly what will happen with a Hyperledger Fabric network, where each of the components which make up the network will be defined within the YAML file, and Docker Compose will be used in order to bring up those components as individual Docker services. So we'll go ahead and run this curl command to download and install Docker Compose. With the Docker Compose binary now available in user local bin, we will need to ensure that execute permissions are available for our current user on that binary. The chmod a+x command will add execute permissions for all users on Docker Compose. The next thing we will do is to install libtool, which is meant to make it easier to create libraries. Again, we won't be handling these tools directly, so we can just go ahead with the installation. And with this complete, all of our installations related to Docker and Docker Compose have been completed. In the next video, we will proceed with the installation of Golang and also update the AWS binary and AWS CLI on this VM instance. In the previous video, we connected to the VM instance which we provisioned earlier, and then we set it up with Docker and Docker Compose. And the next step for us is to install Golang. Hyperledger Fabric is written in the Go language, and we will need to install Golang in order to be able to set up such a network. And we need to execute this wget command in order to download the Golang package. So once we get that, we first confirm that this gzip file has been downloaded. And then following that, we will unpackage this by running the tar-xzf command. We can just confirm what has been unpacked by running ls. And we can see that a new directory called Go has been created. All right, so we can now cd into that to see what it contains. And this is the entire Golang package. This includes the binaries in order to run Go commands. But now I'm just going to cd back to my home directory, which contains this Go installation. And then I'm going to move this Go directory over to the user/local directory on my file system. So with that, I'll clear the screen once more. And the next tool to install is libtool-ltdl-dlevel. This is something which will be used by Golang. So once this installation is complete, we still have a few more steps to go through, which includes the installation of Git. Once that is done, we have set up Docker and Golang successfully, but we do need to make a change to our bash profile. So I'm going to edit this using the Nano text editor. And then from here, we will need to add the Go path as a separate environment variable, and then include the Go root directory in the path environment variable. We also need to include the directory containing the Fabric CA binaries to the path. With that done, I'm going to go ahead and save the changes to the bash profile. And for these changes to take effect without having to log out and log back in, I'm going to make use of the source command. Once we have run this, we have performed all of the prerequisite tool installations which are required in order for us to set up a Fabric network on this instance. At this point, we can confirm the versions of each of these tools which have been set up, starting with Docker. So we run sudo docker version, and In my case, it is version 18.06 which has been installed. We can next check the version of Docker Compose. So I'm going to specify the full path to Docker Compose here and then check the version. And this is version 1.20.0. Now we can check the version of Golang. And on my machine, the version which is installed is 1.10.3. So the reason I print out these versions is in case you run into any issues with compatibility, then you know that these versions of Docker, Docker Compose, and Golang do work with Hyperledger Fabric. At this point, we have all of the tools which we need in order to set up a Fabric network. But in order for us to be able to set it up correctly, we do need a few other tools installed. Specifically, we need the AWS CLI. And I'm going to check the version of the CLI available on this host. So for that, I'll run aws-version. And this is version 1.16.102. Now, this is a somewhat older version of the CLI, and I'm going to set up the newest version. The reason why we need the AWS CLI is because we need to download the certificates which we will use to set up the Fabric network from AWS S3, and that is best done using the CLI. To update the CLI, we will need to install pip, and to do that, I'm going to make use of this curl command in order to download a pip installer. So once this is executed, this getpip.py script is downloaded, and we can run sudo python getpip.py, which will download and install pip for the current user. With pip setup, we will now need to make another change to the bash profile. So editing that with the nano text editor, I will make another addition to the path environment variable. And this is where it can find the binary for pip. So with this change made, I'll go ahead and save this file once more. And then once again, we will source this bash profile. With these changes in place, we can finally upgrade the AWS binary here. So we run pip install --upgrade --user AWS. And with that done, the newest version of the AWS binary has been installed. And at this point, we can also update the AWS CLI using pip install once more. And now, all of the necessary installations have been complete on this VM instance. In the next video, we will need to set it up in order to run with the AWS Managed Blockchain Network which we provisioned. So far, we have set up a Hyperledger Fabric blockchain network using the AWS Managed Blockchain Service. We then configured the VM instance which we provisioned earlier in order to work as client to the Fabric network. The setup is not complete, however, since we need to hook up the client to connect to the blockchain network. And then beyond that, we also need to set up a peer node on the network so that we can install some chain code on it and eventually execute transactions. We will now proceed with the hooking up of the client with the network. And for this, we head over to the AWS console, then over to the services menu, and then from there to the Amazon Managed Blockchain Service. From here, we will need to make note of this network ID which has been generated for our network. So this will need to be used in order to connect our client to this network. So you can copy it down right now or even later on. But for now, let us click on this particular network. This will take us to the home page for the network. And then from here, we will navigate to the Members tab. From here, there is another ID which we need to make note of. So this is an identifier for the organization which is a member of the blockchain network. So we need both the ID of the blockchain network in general and also of this specific member. And this is because we will configure our client to connect to the network via this organization. Heading back now to the shell where I'm still connected to our VM instance, we will now set up the AWS CLI so that we will be connecting to AWS using the credentials of the user we had provisioned earlier. You will recall that this is a user which I had called org1, and to this we had attached a number of different policies. This included the ability to create VPC endpoints and also access to Amazon S3. Now, to configure the AWS CLI to connect to AWS as that user, we need to execute the command AWS configure, and we will need to specify some details for the user. First of all, we will need to specify the AWS access key ID, and you'll recall that this was one of the details which was published when we created our org1 user. I had saved those details down in the CSV file which was downloaded. I'm now going to access that. So this is credentials.csv, and you'll see that this includes the username as well as the access key ID and the secret access key. Copying over the access key ID now, I'm going to go ahead and paste it in the shell. And then we are prompted for the secret access key. So I'll head back to the CSV file, copy that over, and then paste it in the shell. After that, we'll be prompted for some additional details. So I'm not going to specify any value for either the region or the output format. So there won't be a default value for either of those. So the blockchain network, which has been set up so far, includes an ordering service endpoint, but so far it does not have either a peer or a certificate authority endpoint. In order to get the value of the CA endpoint for the organization in our network, we will need to run this command: AWS manage blockchain get-member. To this, we need to specify a few arguments. The first of these is the network ID, and this was the value which we had copied over from the console. And then we also need to specify the member ID of the organization whose certificate authority's endpoint we wish to receive. We also explicitly specify the region for our blockchain network, which is US East 1. Just to quickly revise where we can get the details from, if we head over to the details of the organization, we will be able to get the member ID from here. And then when we navigate to the network section, right next to the name of the network ID will be available. Once these details are copied over and this command formed, we can run it. And what is returned to us is a JSON structure, and the specific detail which we need is this CA endpoint. So do copy this down, because the next step for us is to ensure that the CA endpoint has been configured correctly. So we use curl in order to send it a request, and then we expect that a response will be obtained in return. So when we run this, we do get a rather long response. So if we head back to the network section and click on this network link and then head over to members, we can head over to this org1, and the details of the CA endpoint will be available here as well. So we now know how to access this information from both the command line as well as the console. Heading back now to the command line, now that we know that the Fabric CA endpoint has been set up, it is now time for us to configure the certificate authority. We will now run this go get command in order to download the Fabric CA files from a GitHub repo. Once that is done, we can access this CA package by heading over to this directory location, which is in the Go path. This path, in fact, links up to a Git repo. So when we run git fetch, all of the latest files will be downloaded from the repo. Now the specific branch, which includes all of the files which we need, will be in the release-1.2 branch. So I'm now going to switch into that. And following that, we can run an ls just to confirm all of the Fabric CA files which have been downloaded. Now that we have all of the Fabric CA source files, it is now time for us to build and install the Fabric CA client on this machine. To do that, we just need to run the make file which has been included. So we run make fabric-ca-client. And this make could take a couple of minutes, but once it is done, The Fabric CA client has been built and it is now installed and ready to use on this VM instance. It is now time to take a look at the smart contract, which we will be deploying to our Hyperledger Fabric network just a little later. The main purpose of the smart contract is just to ensure that our Fabric network is functioning correctly, that we're able to install it on the peers in our network and then instantiate it and then use it to record transactions. Now, this smart contract can be downloaded from a Git repo, and I have created my own Git repo for this purpose. So I have created a smart contract in this repo called car store, and we can now go ahead and take a look at what exactly this repo contains. So navigating to this GitHub URL from the browser, we are directed to this repository, and then there is a directory called Go, which is created within it. And it is inside this directory that our chain code is available. I'm just going to click on it so that we can now begin browsing over the chain code. So this is the FabCar chain code, which is available as one of the samples for Hyperledger Fabric. It effectively serves as an inventory of different cars, where you have a collection of key and value pairs, the keys being an ID for the car, and the value being the details of that corresponding car in JSON format. All of the key and value pairs will be stored within the contract state, and there will be a number of different methods for us to be able to add to the contract state and also to retrieve details of the vehicles from there. So to begin, we can start off with the package definition. So this is going to be part of the main package. And then following that, we have all of the different packages which we need to import into this chain code. I won't go into great details for each of these packages, since we mainly need to understand at a higher level what this smart contract does. Packages such as bytes and strconv, for example, will help us convert certain data into a specific format. But the important package here is the chain code shim package. This includes a number of different interfaces which allows us to access the contract state. The peer package at the end will be used in order to capture the responses coming in from the peers when we submit transactions to them. So we begin by defining a smart contract type, and this is going to be an empty struct. We will be attaching methods to this particular smart contract type later on with the use of receivers. In case you're not familiar with the Golang language, there are no classes with associated functions in Golang, and one way to kind of mimic this behavior is to have this kind of struct where you attach functions to it by means of receivers. We now move along to the data which will be stored in the contract state. So I mentioned that it's going to be a collection of key and value pairs, and the values will be of this car struct type. So you can see the details which we store for each vehicle include its make, its model, the color, and the owner of the vehicle. Which takes us now to the first of the methods in our smart contract. And this is where we specify the smart contract type to be a receiver for this function. This means that this particular function will be attached to the smart contract struct, and the specific function in this case is the init method. So this is a function which needs to be implemented in any Hyperledger Fabric chain code. The argument to this is of type shim.chaincode_stub interface, and this is one which can be used in order to interact with the contract state, for example. The value returned by this function is going to be a peer response. SC here is an alias for the peer package which we have imported. So the init method is one which is called when we initialize a smart contract. And on this occasion, we don't really return anything other than a success message. We use the shim package to do this. So this concludes the definition of the init function, which is one of the functions which we need to implement, and the other one being the invoke function. So each time we submit a transaction or query the state of our blockchain, we end up making a call to this invoke method. This effectively serves as an umbrella for different functions defined within our chain code. So the arguments to the invoke method will include the name of the function in the chain code which needs to be triggered along with its arguments. So we can retrieve these values by making use of the shim.chaincode stub interface. And then following that, we will explicitly call the function which has been passed along to this invoke method. So note over here that we are effectively calling the query car function, which is going to be defined just a little later in this chain code. And the arguments we pass along to this include the API stub, along with the arguments for that function, which were passed along to invoke. It is quite common to do some kind of pre-processing of the function arguments before making a call to the function within the invoke operation. But in this case, we simply call the query car function directly. Similarly, if it is the Init Ledger function which the user wishes to invoke, then we just directly call that function. So this is a function which doesn't take in any arguments, so we only pass along the API stub. And if the invoked function is the createCar function, then it is createCar which will be called along with its arguments. There is also a function called queryAllCars which has no parameters, and there is one called changeCarOwner as well. All of these functions will be defined just a little further down in this chain code. Now, if the invoke operation is triggered and the name of the function which is specified is one which does not exist within the smart contract, then an error will be thrown. So this concludes the definition of the invoke method for our chain code. And it is now time to go ahead and define each of the individual functions which were called from invoke. In the previous video, we started off taking a look at this car store chain code, which will serve to store an inventory of different vehicles. We took a look at the init and invoke methods, which are the two functions which need to be implemented in any Hyperledger Fabric chain code. There are a number of different functions though, which this chain code includes, and we will now take a look at each of them. The first one is called query car, and as the name implies, this is one which will allow a user to query for the details of a specific car. The ID of that car needs to be provided as an argument, and though the arguments are an array of strings, the length of this array needs to be exactly 1, so that only one ID is passed along. Then, in order to retrieve the details of the car, the API stub variable is used, and specifically its getState method is called, which will return the value corresponding to a particular key from the contract state. So here we pass along the input argument as the key whose value needs to be retrieved. So this concludes the query car function. And the next one in our chain code is called Init Ledger. This one will initialize the inventory with the details of 10 different vehicles. This one does not accept any arguments, since the vehicle information is all hard-coded here. So here the details of all the vehicles are stored in an array called cars, and then following that, we iterate over the array and then add the details of each car to the contract state. When we do that, we generate an ID for each vehicle and then use the API stub.putState method to add a key and value pair to the contract state. The key here being the car ID and the value being the car information in JSON format. And at the end, we return a success message. So while the query car function is meant to retrieve the details of a specific car from the contract state, the createCar method will be used in order to add the details of a single vehicle to the state. Once again, the putState method of the API stub variable will be used for this, which takes us along to the next function, and this is called queryAllCars. This one does not take in any arguments, and when it is invoked, the details of all of the cars which are stored in the inventory, that is in the contract state, will be retrieved. Now, it's not strictly all of the cars, specifically those which have an ID between 0 and 999, as specified by the smart key and end key variables, will be the ones whose data is returned. Note that in this function, we make a call to the API stub.getStateByRange method. So we don't need to make multiple calls to the contract state in order to retrieve a range of values, and we can use this method as long as the key is defined in a specific format. The value returned by this getStateByRange will be a collection of iterable results, and by making use of the defer keyword, we can ensure that this iterator will only be closed once the queryAllCars function is finished executing. Since the results returned by this function can be rather large, we will need to initialize a buffer before returning it. And then we iterate through all of the results and then go along and add them to the buffer. Before the data is printed out, it will be formatted into a JSON-like structure. But at the end of it, we will return a success message. And then we move along now to the last of the functions in our contract, which is called change car owner. This accepts a couple of arguments as well, which include the ID of the car whose ownership needs to change, as well as the name of the new owner. So there are two arguments which we expect. And if everything is entered correctly, we will first retrieve the instance of the car which is stored in the contract state. Following that, we will set the value of the owner for that car object to the new owner, and then we will update the state with the new car object. So this is the change car owner function defined. And now all we need to do for our chain code is to define the main method. This is what will be called when we instantiate the smart contract. And all we do here is to create a new instance of the smart contract struct. So with that, we conclude the definition of this chain code, which serves as an inventory of vehicles. At this point, we can return to our VM instance. And then from here, we execute the git clone command so that the chain code is downloaded into this instance. So far, we have set up a Hyperledger Fabric network using the AWS Managed Blockchain Service. And beyond that, we configured a client, specifically a Fabric CA client, on this VM instance. We have now downloaded the chain code which we eventually wish to deploy to the Fabric network. But in order to perform the chain code installation, we will need to make use of the Hyperledger Fabric CLI. Hyperledger supplies to us a Docker image which can be used to run a CLI container, and it is from within that container that we can run the commands in order to interact with our Fabric network. So let us now take a look at this directory. In my case, it is the home directory on my VM instance. And this includes a number of the files which we have downloaded during this course, as well as the car store directory, which includes the chain code which we will deploy. We will now set up a docker compose.yaml file in which we will define the CLI container which we wish to bring up. So I'm now going to use the nano text editor to create this file, which is called docker-compose-cli.yaml. And within this YAML file, I'll go ahead and paste the contents. So here we are defining a Docker service, and this service will run a single container for the Hyperledger Fabric CLI. The image out of which this container will be built is hyperledger/fabric-tools, specifically version 1.2.0 of that image. I won't get into the remaining details, but we'll just go ahead and save this Docker Compose file. And then in order to bring up the CLI container, we will need to run this docker compose up command, where we specify the name of the YAML file, which contains the definitions of the services which need to be brought up. We also specify the -d option so that the containers will be brought up in the background, that is, in detached mode. So when we run this, our CLI container should be created, and we can confirm that by running docker ps. This lists all of the running containers, which includes the CLI container, which in my case has been up for about 14 seconds. With the CLI container up, it is now time for us to set up an admin user for this organization. Doing that will require us to use an X509 digital certificate. For the purposes of this demo, I'm going to make use of a sample certificate provided by AWS for specifically this purpose, to test out the AWS managed blockchain configuration. This certificate is available on an AWS S3 bucket, which is why we required the user, which we provisioned earlier, to have S3 access. So the command to run in order to download a file from an S3 bucket is AWS S3 CP. The first argument is the source of the file which needs to be copied over, which is a link on an S3 bucket. And then the second argument is the location on our local file system to which the file will be copied. Once that is done, we should have the certificate on our local file system, which we can confirm by running ls. And we now know that this certificate is available locally. To view the contents of the certificate in a human-readable format, we can make use of this openSSL command, and this will return to us the details of this certificate. Now, you can make use of your own certificate as well, or you can use this sample certificate just like I am. But once you're ready, we can enroll an admin user whose identity will be represented by this digital certificate. The command to run for that is fabric CA client enroll. The arguments which we specify include the URL of the fabric CA server, and note here we are specifying the credentials of the admin user which we provisioned at the time of setting up the AWS managed blockchain instance. So org1 admin is both the name of the user as well as its password, and after the @ sign we specify the CA endpoint for our organization. And then we make use of the tls.certfiles argument, where we will pass along the certificate which we have just downloaded. And the final argument is the MSP directory. And when we run this, we have enrolled a new user to the organization in a Hyperledger Fabric network. We can now view the contents of the admin-MSP directory, and the output shows us that a certificate is now available in the sign search directory. Now this represents the user we have just enrolled, and in order to make them an administrator for this organization, we will need to copy that certificate into the admin-MSP/admin search directory. Since the admin search directory does not yet exist, we are effectively replicating the sign search directory and all its contents to create this admin search directory. So we run this and then view the contents of admin-MSP once more, and that cert.pem file is now available in admin search as well. Alright, so we now have an administrator for our organization, and it is time for us to move along to the console and then create a new peer node for this organization. So we're almost there. When we click on create peer node, we will be prompted to enter details of this peer. So you select the instance type, and I'm going to select one with 2 vCPUs and 2 gigs of RAM, and this will be provisioned in the US East 1A zone for me. And once that is done, we can go ahead and provision this node, and you can see that it is still in the process of being created. This may take a minute or two, but you can click on that node in order to view the details. But this is still being provisioned, so I'm just going to wait. And once it's done, you should be able to see the status reflected as available. So clicking on this once more, we can see that the details now include a peer endpoint, a peer event endpoint, as well as a node ID. Now with the peer node provisioned, it is time for us to set up a channel on our Fabric network. And that is what we will be doing in the next video. Now that we have set up a peer in our network, we can go about creating a channel to which we can connect the peer. The way to define a channel is to make use of a configstx.yaml file. I'm now going to create this file using the nano text editor, and we'll go ahead and paste the entire contents of the file. And we can now walk through each of the blocks one by one. So I'm first going to scroll all the way to the top. And then at the very top, we have the definition of organizations which are part of this channel. So this is a block called organizations. And the first org which we define is called org1. The ampersand symbol just before org1 signifies that this is a block which can be referenced later as org1 within this file. Within this org block definition, the member ID for this organization is included in both the name as well as the ID fields, whereas the MSP directory is also set here. The anchor pairs are ones which will be used for inter-org communication, but since we only have one org, we'll leave it blank for now. Moving along to the applications block, we will just leave it as is. And then at the end, we define the profiles where we define the contents of the channel on this Hyperledger Fabric network. So this is a channel called OneOrg channel, and it represents a consortium called AWS System Consortium. The channel includes an application configuration, which can also include a number of organizations. Here we reference the org1 block which we defined previously using the asterisk followed by org1. What we're defining here is a channel which includes the single organization on our Fabric network. With that done, we can save this file. And what we will need to do next is to initialize a channel configuration based on the contents of this configstx.yaml file. The way to do that is to run a binary called configstxgen, which is available on the CLI container. So we can run docker exec CLI configstxgen, followed by the arguments to configstxgen. The output create channel tx argument specifies a file to which a transaction for the creation of the channel can be written to. The profile argument specifies the profile within the configstx.yaml file, which represents the channel definition. The OneOrg channel in our profile represents a channel containing a single organization. The channel ID is the ID for the channel, which has been set as my channel, but later on in this course, I'll be using an identical channel called channel1. And finally, the config path argument specifies where the configstx.yaml file can be found. When we execute this, the transaction in order to set up our Hyperledger Fabric channel will have been initialized, and this will be written to a file which has the extension .pb and bears the name of your channel. So at this point, pretty much all of the configurations which we require for our Fabric network have been complete. And to use this VM instance as a client which can invoke transactions, we will need to add a few environment variables to the bash profile. So I'm now going to edit this. And in addition to what we have added to it already, I'm going to include a few additional environment variables. Starting with the msp_path variable, which will point to the location of the admin-msp directory. Next, we will specify the MSP ID for this particular organization. And just as a refresher, in case you forget where this detail can be obtained, we can head back to the console and access this Fabric network. Head over to members, and the ID for each of the members in our network should be available here. Right now, there is just one member, so we copy over this membership ID and then enter it as the MSP environment variable's value. The next thing we need to do is to specify the endpoint of the ordering service for our network. So I'm now going to paste this particular value here. And in case you're not clear where this value can be obtained from, we head back to the console and over to the details tab for our network. And this is the location where that ordering service endpoint can be found. Now, when we invoke any transactions from this client, we will need to submit it to a peer. And with this peer environment variable, I'm supplying the endpoint of the local peer. Once again, in order to retrieve this value, we head back to the console and over to members, heading over to org1, where we can view the details of all of the peers which are part of this org. We click on the peer, and then from the details, we can collect the value of this peer endpoint. So you can copy this over and then paste it in this bash profile. I'll go ahead and save the changes to this file. And then you can also run source on the bash profile so that all of the environment variables will be initialized. So with the environment variable set and the channel configuration transaction available in the .pb file, we are now ready to create the channel. So we'll need to run the command from the CLI container, for which we make use of the docker exec command, which is followed by all of the environment variables which we need to pass along to the CLI container. This includes a flag to enable TLS for communication with the peer node, followed by the environment variables which we have set up. This includes the MSP_path, the MSP, and the peer environment variables, which are mapped to core_peer variables on the CLI container. We also specify the location of the TLS root certificate file for the peer. So once these environment variables are passed along to the CLI container, the specific command which we execute from its shell is peer channel create. With the -c argument, we specify the name of the channel which needs to be created, which is channel 1, and the transaction in order to create that channel is available in the channel1.pb file. When creating the channel, we also need to specify the location of the ordering service. So the -o option is followed by this ordering service endpoint, which is available in one of our environment variables. The arguments also include the CA file, and we also specify the TLS flag so that TLS is used when communicating with the ordering service. And running this should create this new channel. Running this command will have created a file called channel1.block in your current directory. This file represents the genesis block for your channel. The channel is still not ready, however, since we need to join a peer to the channel, and the command to execute for that is peer channel join. In order to run this on the CLI container, we once again run the docker exec command and pass to it the same environment variables as we did previously. And then we run the peer channel join command, whose argument includes the genesis block which was created when running the peer channel create command. We once again specify the orderer, and for this we make use of the orderer environment variable, and then we also pass along the CA file. And when we execute this, our peer has successfully joined this channel. And with that, our Hyperledger Fabric network setup is now complete. We have provisioned the Fabric network using AWS Managed Blockchain, and that included an ordering service as well as an organization which had a certificate authority. We were then able to add a peer to that organization and then join that peer to a channel. And now that we do have a channel with its own genesis block, we can record transactions on that channel. But first, we will need to deploy our smart contract over to it. And that is what we will do in the next video. We have now successfully set up a Hyperledger Fabric network, which includes one peer in an organization, which we have joined to a channel. In order to record transactions on the network, we will need to install our chain code to it. And the way to do that is to run the command peer chain code install. This again needs to run from the CLI container. And to know which peer that particular peer command pertains to, we need to set the value of the core_peer environment variables accordingly. So to run this command from the CLI container, we use the docker exec command. And then, as we did before, we pass along these environment variables, which make sure that the peer binary references this particular peer, which is the one which we created in our organization. And the command we run is peer chain code install. We also pass along 3 arguments to this command. The first one, with the N flag, is the name of the chain code, which we have called mycc. We then specify the version for the chain code, which I have set to v0. And then following that, we need to specify the directory in which the chain code sources can be found. Do note that this directory location is one in the CLI container. And in our Docker compose file, where we define the service for the CLI container, we had mapped the directory containing the chain code sources on this EC2 instance, which is the host machine, to this directory in the Go path in the CLI container. So once we run this chain code install command, this will have installed the smart contract onto the peer which we have in our organization. Do keep in mind that the installation of chain code happens at the level of individual peers. So if you happen to have multiple peers which need to be able to access the chain code, then the installation will need to be performed individually on each of them. Well, the installation of the chain code is just one step towards the full deployment of the smart contract. And the next step for us is to instantiate the chain code. Now, while the installation occurs on a per peer basis, the instantiation of chain code occurs per channel. The command to run for this is peer chain code instantiate, and we once again run this from the CLI container, and we point this to the peer in our organization by means of the environment variables once more. So the arguments to this peer chain code instantiate include the orderer for the channel as well as the name for the channel, followed by the name of the chain code which is being instantiated, which in our case is mycc, then the version of the chain code, which is v0. And because the peer chain code instantiate command calls the constructor of the chain code, which is the init method, it is here where we can specify the arguments which we want to supply to the init method. In our specific chain code though, there are no such arguments to init. So after the -c option where we can list down all of the arguments which we wish to pass, the args array is empty. We finally, when we invoke this transaction, we make use of the CA file and enable TLS. And once we execute this, our chain code will be instantiated and will be ready for us to use and record transactions. So just to reiterate, the installation of a chain code happens at the level of individual peers, whereas the instantiation of chain code happens per channel. To confirm that this smart contract has been instantiated, there is another peer chain code command which we can execute from the CLI container, and this is peer chain code list. When we execute this command, we make use of the instantiated flag so that this will return all of the chain codes which have been instantiated on the given channel. And when we run this, we can confirm that mycc version v0 has been instantiated on channel 1. Alright, so we are now finally ready to record transactions on our blockchain by invoking functions from this instantiated chain code. Now, the invocation of the functions in our smart contract happen via the invoke method, which effectively serves as an umbrella function. In order to call the invoke method, we can run the command peer chain code invoke, and once again we do this from the CLI container. And as with the previous peer commands, we pass along the environment variables which will point the peer binary to the one peer which we have in our organization. Now, when invoking peer chain code invoke, we need to specify in the arguments the name of the channel on which the chain code has been instantiated, which is channel 1, followed by the name of the deployed chain code, which is mycc, and then after the -c option, we specify in a JSON structure the name of the function to invoke, followed by the list of arguments for that function. In our case, the function we are invoking now is Init Ledger, and you will recollect that this loads the data for 10 different cars into the state of our chain code. The data for all of those cars were hard-coded in our smart contract, which is why this specific function does not require any arguments, and the args array is empty as a result. So when we invoke this pure chain code invoke command, this seems to have gone through smoothly. And because this operation involved writing data to the contract state, it invoked a transaction. Now, to confirm that this data has indeed been written, we will need to query our chain code. And for that, we will need to invoke one of the other functions defined within our smart contract, specifically the query all cars function. Now, this is a function which only reads from the contract state, which is why the command to execute in this case is not pure chain code invoke, but pure chain code query. Executing this will not update the blockchain and no write operation will be performed. So just as with the invoke operation though, we need to pass along the name of the channel and the chain code, followed by the arguments, which includes the name of the function which we are calling. With the pure chain code invoke command, we need to pass along the name of the function and the arguments separately. But in the case of the query command, the arguments array includes the function name as the first element, followed by its arguments if it has any. So when we execute this command, all of the 10 cars which we had loaded by calling the Init Ledger function are returned. So this is clearly a testament to the fact that we have set up our Hyperledger Fabric network correctly. We have been able to successfully deploy chain code, and then following that, we have been able to invoke transactions and also query data from our chain code. We'll continue with the tests, however, and we will now invoke one of the other functions defined within our chain code, and this is the createCar method. Since the createCar function involves writing to the state of the contract, we will need to execute the pure chain code invoke command. This time, when we specify the arguments, we specify in the function field that this is the createCar function, and then the args field includes the 5 different arguments which are required in order to create a new instance of a car. Car 10 is the ID of the vehicle, and this happens to be a black Toyota Prius owned by Alice. So when we run this command, the status reflects that this was a successful operation. And of course, there is one way to confirm that this has been written to the blockchain state, and this is by calling query all cars once more. And this time, within the results, we will need to search for this new vehicle, but this car 10 record confirms that our invocation of createCar was also a success. While these are the operations which I'll cover in this video, do feel free to test out some of the other operations as well, and then make sure that your contract works as expected. In this exercise, you will start off by describing the voting policy for a network on the AWS Managed Blockchain Service. When setting up a blockchain network using this service, we saw during this course that we will be asked to configure the voting policy. There are a couple of details which need to be specified, and you will need to recall what exactly those are and the different permutations which are possible with those configurations. Next, you will list down the 2 methods which need to be implemented in any Hyperledger Fabric chain code. When developing the smart contract to be deployed on the Hyperledger Fabric network, we saw during this course that we could implement a number of different functions. Out of those, however, 2 functions absolutely need to be implemented in any chain code, and you will need to recollect what exactly those are and what purpose they serve. Since both of these topics were covered during this course, you can pause this video and then take some time to perform each of these tasks on your own. For the first task, you needed to recollect the details of the voting policy which is configured when setting up a blockchain network on AWS Managed Blockchain. Well, the main purpose of the voting policy is to stipulate the requirements for the approval of a proposal. A proposal is something which is brought up by any member of the blockchain network in order to either invite an additional member to the network or to remove one of the existing ones. The network set up on AWS Managed Blockchain has some kind of a democratic touch, where the proposal involving either the invitation or the removal of a member is subject to a certain percentage of yes votes. This means that the proposal is only approved if a certain percentage of the existing members of the network vote yes on it, and the percentage of yes votes required can be configured in different ways. For example, it can be set to be greater than or equal to the specified threshold, or alternatively, you can set it to be strictly greater than that threshold. The default policy is that the proposal is considered approved if greater than 50% of the existing members approve of it. However, it's not just the percentage of votes which will allow a proposal to go through, since the yes votes of a proposal need to come in before a specified time, and this is where the duration of the proposal comes into the picture. So once a proposal has been created, it can be set a duration, and this varies from a minimum of 1 hour to a maximum of 168 hours or 7 days. The default setting for the proposal duration is 24 hours. So the voting policy on the AWS Managed Blockchain Service stipulates a minimum percentage of yes votes in order for a proposal to go through, along with an expiration time for all proposals, by which the required percentage of yes votes must be gathered for the proposal to be considered approved. For the final task in the exercise, you needed to list down the two methods in any Fabric chain code which need to be implemented. One of these is the init function in a smart contract, and this is the function which is called when you initialize the chain code. This effectively serves as a constructor, and the init function is able to accept arguments just as any constructor in an object-oriented language. When running pure commands from the shell, the init function is effectively triggered by running the command pure chain code instantiate. The second function which needs to be implemented is the invoke function. Now this effectively is an umbrella for the invocation of the different methods defined within the smart contract. So the chain code functions are not called directly, but by means of the invoke function, where you can perform some pre-processing of the arguments to the function being called. The invoke function can be triggered by two different pure commands. One of these is the pure chain code query command, which is used to call functions which are read-only. That is, they don't make any changes to either the contract state or to the blockchain. On the other hand, if the function does alter the state of the blockchain or the contract, then this will involve a transaction, and the way to create one from the CLI is to run the pure chain code invoke command. Whether running query or invoke, the arguments include the name of the function which is being triggered from the contract, along with its arguments. So far in this learning path, we have successfully set up a Hyperledger Fabric network using the AWS Managed Blockchain Service. The network we set up, however, involved just a single organization, and the purpose for setting up a Fabric network is to typically involve a consortium of organizations who can work together and then record their transactions on a blockchain. We will now see how we can extend that one organization blockchain network to include a second org. This requires access to a second AWS account who can be invited to join the Fabric network which has already been set up. The second account need not necessarily belong to a different organization, but could also be a different department within the same org. But let us now proceed with the demo. So I'm currently logged in to the AWS Management Console as a user called cloud.user, which belongs to the first organization in our Hyperledger Fabric network. We can navigate to the account details for this user by clicking on this and then heading over to my account. And you will observe that the details include an account ID. When inviting a new member to join the blockchain network which has been set up, we will need to make use of their account ID. Now that we know how to retrieve this information, I'm going to close out of this tab. And on my other tab, I'm currently logged in as a different user on a different AWS account. So this is one called dev user, and you can assume that this belongs to a different organization or could also be a different department in your own org. You can see that this particular user has a different account ID. And in order for this particular account to be joined to the already existing Fabric network, the account ID will need to be passed along to the first org. At this point, I'm going to close down this tab. And what we will need to do for this organization to be ready to work with that Hyperledger Fabric network is for it to have its own Fabric client. To do that, this organization will need to create its own EC2 VM instance. And then for that, it will also need to have a user who will have permissions similar to what we had previously for the user on org1. So we'll now go ahead and set up this user, for which we head over to the services menu and then to the IAM dashboard. Now we'll have to repeat the steps which we did for the user on org1. So we'll need to create a policy, for which we head over to the policies dashboard and then choose the option to create a new policy. Just as we did before, we head over to the JSON tab and then we paste in the JSON for this policy, which allows the creation of VPC endpoints. We'll move ahead to the next step where we set a name for this policy. And this is going to be the same as we said previously, creating and managing VPC endpoints. Following which, we can quickly review the policy details and click Create Policy. So with our custom policy set, we will go ahead and create the new user. So heading to the users dashboard and clicking Add User. This user will be called org2. And then we also wish to enable programmatic access for this one. So I'm checking this box. And then we move along to the permissions. We head over to the Attach Existing Policies section. And then we will need to search for the policies which we have created. So this is the creating and managing VPC endpoints, which I'm going to check. And then this user will also have the Amazon S3 full access. Then we also need to give permissions for the Amazon Managed Blockchain Service. So I'm giving full access to the console. And then also full access to the general AWS Managed Blockchain Service. All right. So we proceed to the next step where you can attach tags if you wish, but I'm just going to skip that and move straight to the step to review the details of this user. Here we can confirm that all the 4 policies which we had selected have been attached correctly and then choose to create this user. So now that our second user has been created for org2, this user will need the access key ID and the secret access key if they are to have programmatic access, and they can copy it from this UI here, or they can just download the CSV file. Heading over to the location where this file has been downloaded, I notice that this has been named as credentials1.csv. Since I already have the credentials.csv for org1, so I'm going to rename this file and call it credentials_org2.csv. And then I'll also rename the other credentials.csv to reflect the fact that this contains the credentials for org1. So with these credentials in place, we can now close out of this particular page in the console. And now that this org2 user has been set up, this user will also need to provision an EC2 instance from which to run the client and also attach a security group to it, which will enable access to that instance via SSH from our machines. So once more heading over to services and then EC2, the first thing we will do from this dashboard, which currently doesn't have any instances, is to create a security group. There is already a default security group which has been set up here. But since that doesn't serve our purpose, we will go ahead and create a new security group, and we'll populate the details just as we did previously for org1. So this once again will be called HF client and endpoint. We'll add in a description. We'll associate this security group with the default VPC for the account. And then we can go ahead and hit create. It is now time to define the inbound rules for this. So once we select this security group, we head in the menu at the bottom to inbound, and then choose to edit this inbound rule definitions for the security group. Just as with the first organization, the first rule we will set up is to allow all traffic between any instances which have the security group attached. The next rule we will add is, of course, to allow SSH connections from our own machines to those instances which have this security group attached. And the reason why we restrict the source to just our own IPs, even for the demos, is in order to prevent attacks from bots. This is a common problem when one doesn't restrict the sources of incoming connections to their VM instances. So with the inbound rules defined, we can go ahead and click Save. And with that, our security group has been set up, which includes these two inbound traffic rules. We can quickly confirm the outbound rules as well, which should allow unrestricted outbound traffic. So with that, our security group has been set up. We can head over to the description tab just to confirm the details for the security group. And now we will go ahead and set up the VM, which will serve as the client for this second organization for the Hyperledger Fabric network. So I'm now going to head over to the Instances menu in the EC2 dashboard. The setting up of this instance will happen in the next video. In this demo, we are in the process of setting up a second organization which can connect to the Hyperledger Fabric network which we set up previously. So far, we have provisioned a user as well as a security group, and it is now time for us to set up a VM instance which will serve as the client for the second organization. From the EC2 Instances dashboard, we pick the option to launch a new instance. And once again, we will need to select the image out of which this instance will be built. And I'm going to select this Amazon Linux 2 AMI again. For the instance type, we can stick with the T2 micro instance, which includes 1 vCPU and 1 gig of RAM. And then we can move along to configuring the details for this instance. Now, again, I'm only going to create a single instance, and this will belong to the default VPC for this account in the second organization. As for the subnet, I'm going to leave this as no preference, and then leave the auto-assigned public IP as the default as well, where an IP will be assigned. Following that, all of the other details I'm going to leave as they are, and then move ahead to the next step. This is where you can specify the details of the storage to assign to this instance, and once again, I'm satisfied with what is provided as default. Moving ahead to the tags, I'm just going to skip right ahead since I don't want to attach anything to this instance. And this is where we can attach the security group which we created to this instance. So I'll pick the option to select an existing security group, and the one which we just provisioned earlier will be attached to this VM. So now we can review and launch this new instance. So we can just quickly verify all of the details here and then proceed to the launch button. So we are again prompted for a key pair which will be needed to connect to this VM, and I'm going to generate a new key pair for this one as well. This I will call org2-key, and then choose to download this key pair. Alright, with that done, we can go ahead and click Launch Instances. So we now have a second instance which will serve as the client for org2 in the Hyperledger Fabric network. We can now view the details of this instance, and I'm going to fast forward until this instance gets into the running state. we can view all the details for this instance, and scrolling all the way to the right, you can see the AWS account ID which owns this instance. So this account is now all set up to join the Hyperledger Fabric network. So in order to view if any invitations have already come to it, this account can head over to the services menu and then over to Amazon Manage Blockchain. Since this particular account has not created a blockchain network yet, it will be taken over to this dashboard, which prompts the user to create a network. But to view the invitations, we can just edit this URL where we replace first run with invitations. And it is from this page where the account can view the different invitations which are available to it. Now, this particular invitation is not the one from the network called Fabric-Network, which we had set up previously. So the user from org1 will need to explicitly send over an invitation to this particular AWS account. Let us see exactly how that works. I have now switched over to the tab where the user from org1 is logged into the AWS Management Console. This user will need to head over to Services and then Amazon Manage Blockchain. And they are already part of this Fabric-Network blockchain network. And you can see that this is a Hyperledger Fabric network version 1.2. And in order to invite new members, we will need to click on this link. And while this page gives us all the details of this network, to view the members who are part of it, we'll head to the Members tab. And currently, there is just one member from org1. And then there are no additional members who are not owned by this particular organization. So to fix that, we will head over to the top where we can create a new invitation proposal. When we click on this button, we'll need to fill in a few details for the proposal. Firstly, we can specify the network user who will be submitting this proposal. And in our case, this is org-1 with this member ID. We can also specify a description if you wish. And at the bottom, we will need to specify the account ID of the account which we are inviting to this network. Since we have already covered how this information can be obtained, we will assume that org2 has already forwarded their account number to this particular organization, and org1 will then be able to paste this account ID in the proposal in order to extend the invitation to org2. Now, in this interface, it is also possible to add multiple accounts to this invitation proposal. But in our case, there is just this single organization we wish to invite to the network. So we'll just proceed to the Create button. With that, this invitation proposal has been created, and there is also a proposal ID which has been generated for this. You can see that there is an expiration date for this proposal, which is by default 24 hours from the time the proposal was created. To view the details for the proposal, we can click this link. So there is this proposal ID, and within the details, you can see in the status that this is still in progress. Scrolling further down in the action section, this confirms that this proposal is meant to invite a new account to the Fabric network. You can also have proposals to vote existing members out of the network. Further down, there is a summary of the voting for this proposal. You will recall that the voting policy which we had set up for this network was a simple majority, which means that for a proposal to go through, more than 50% of the existing members of the network must vote in favor of that proposal. In this case, however, since we only have a single organization in the network, there is just one vote which counts. And the summary here shows that there are no yes or no votes yet, and one vote is still outstanding. In order to view the details for the vote, we can expand this particular menu. And for now, there are no details to display here. Now, since this particular network just has a single organization which is part of it, this user will need to supply the vote for their own proposal in order for the invitation to be approved. So at this point, I'll just scroll up, and from this proposal view, we'll head over to the Fabric network view. When we head over to the members, we can confirm that there are no members who have been added yet, and there is no place for us to vote for the proposal. But when we head over to the Proposals tab, we can see the details of this active proposal right here. And when we click on it, we have the ability to vote for this proposal. So for this AWS account, there is just one org which they can vote as. So this is going to be org-1. And then following that, the details of this proposal are visible here, which includes the fact that the actions which are included in the proposal is meant to invite this particular account to the Fabric network. And the voting summary is also available right here. However, in order to cast the vote, we will need to scroll back up. And at the top right, we have the ability to vote yes or no for this proposal. Note here that if there are multiple members in this Fabric network, each of them will be able to vote on the proposal. But in our case, it is the one who is extending the proposal who gets to vote on it. So we will just vote yes here, following which we will be asked to confirm our vote. And at this point, we will just hit confirm. And with that done, this proposal has been approved. So this AWS account, which represents org-1 on the Hyperledger Fabric network, has extended an invitation to the account representing org-2. The invitation was extended by first creating a proposal, and for that invitation to reach the invitee, the proposal needed to be approved. The voting policy which we had set was that at least 50% of the existing members need to supply their approval, and that proposal effectively got 100% approval by means of the single vote which we just recorded. With that done, we can see that this particular proposal is still in an active state. This is because the updates have not quite filtered through, but when we click on this particular proposal, we will be able to view that the status is now approved. Scrolling further down, we can view in the voting summary that one yes vote has been recorded and that there are no votes or outstanding votes. To view the details for the vote, we expand this view. And from here, we can see that this yes vote came in from org-1. So now that we have the details for this proposal here, we head over to the members. And at the moment, there is just one member who is still part of this Fabric network. The reason for this is that the approval of the proposal means that the invitation has been extended to the invitee, but that account has yet to accept the invitation. To do that, we will now need to switch over to the view for org-2. I'm now in the AWS Managed Blockchain dashboard for org-2, and you will observe that the invitation to the Fabric-network is now visible here. Scrolling further to the right, we can see in the status that this is still pending, and this is because this is an invitation which has not yet been accepted. And to do that, we will first need to select this network, and then the three buttons at the top will become enabled, where we have different options. Firstly, we can view the details of the invitation, so we can click on that, and here we can see exactly which network we are being invited to, the specific framework which is being used for the network, which is Hyperledger Fabric version 1.2. And we also have other information such as the number of members who are currently part of that network, the voting policy, and the proposal duration, and so on. Heading over to members. From this view, we can see who are the members from our current organization who are part of this network, which is none at the moment. And then scrolling further down in the members owned by others section, we can see all of the other members of this network. So these are ways in which an organization can verify that an invitation which has been extended to them is a legit one. So once they're satisfied with all of these details, we can scroll further up and over to the invitation section. And then we select this Fabric network once more, which enables the three buttons at the top. So we have the option here to reject this invitation, but what we're going to opt for is to accept it. When we click on this button, we will be prompted to enter the details which will allow this organization to enroll in the Fabric network. So in the member name section, we can identify ourselves here. So this particular organization will call themselves org2, and scrolling further down, they will be able to set up their own Fabric certificate authority. So here the administrator for that can be set up, and this is going to have a username and password of org2admin. So this particular organization will be able to issue their own certificates, which can then be used to interact with this blockchain network. So at this point, the details have been entered, and we can click Create Member and Join Network. And with that, the details for this organization will be getting populated, and this once again could take several minutes. Now, when we head over to the network section, you can see that the Fabric network status is now showing up as available. Heading over to the invitation section, we can see both of the invitations still here, including the one for Fabric network. So that has yet to disappear. But what we're interested in is to head back to the network section. And then from here, we will click on the Fabric network to view its details. We can now see that there is a VPC endpoint service name which is currently set up, but we will need to create a VPC endpoint separately later. And the different details for the network, including the ordering service, are all available here. At the bottom right, you can also see that the number of members in this network have now gone up to 2. So to get the details for these members, we head over to the Members tab. And now we can see both org1 and org2 appear in this view. Since we are connected from the org2 account, we can see that in the Members Owned by You section, and the Members Owned by Others includes org1. And to view the details of org2, we just click on this. And this particular organization is still being set up. Since this can take a while, I'm just going to fast forward here until there'll come a point when all of the details will get populated and the status will be available. So you can see on the right that the Fabric Certificate Authority endpoint has been generated for this organization. And we can use that in order to create the admin user and create additional identities beyond that. It is now time to create a VPC endpoint for this network. So we head over to the network section and then click on Fabric-Network. And then from here, we will click on the Create VPC Endpoint button in the right. So this is a form similar to what we have seen previously, where the VPC Endpoint service name is already available. And we will just specify the VPC for which this endpoint is being created, which is going to be the default VPC in my case. We'll go ahead and specify the subnet and then the security group as well. For this, we will need to specify our own custom security group. With that done, we can go ahead and hit create, and the VPC endpoint has been set up for org2 on this Hyperledger Fabric network. So we now have the second organization connected to the Hyperledger Fabric network. Now for this org2 to be able to send transactions over to the network, it needs to configure a client, and this is where we need to connect to the EC2 instance and then set it up to make use of Fabric CA. And then just as we did with org1, we will need to set up a peer node for org2 and then run peer commands from a CLI container running on the EC2 instance, which will serve as the client for org2. So now that this Fabric network is available in org2, let us go ahead and set up its client, for which we head over to Services once more, and then to the EC2 dashboard. From EC2, we head over to Running Instances, and the instance we provisioned earlier is now in the running state, and what we need to do now is to connect to it. So I brought up this connection page, and just as we did previously, we need to make use of the key file which was downloaded in order to connect via SSH to this EC2 instance. First, we'll need to ensure that the key file has the correct permissions. So I'm now going to head over to the downloads directory on my file system, where I have all of the connection related data stored. So running an ls here, there are two CSV files containing the AWS access key and the secret key ID for org1 and org2. And there are also these PEM files which contain the private keys, allowing us to connect to the respective EC2 instances. I will now modify the permissions of this org2-key.pem file so that I have read permissions and it can be used to establish an SSH connection. And then following that, we'll run the SSH command. This will use the org2-pem file to connect to the EC2 instance we provisioned for org2. Since we are connecting to it for the first time, we will be prompted whether we wish to continue, and I'm just going to hit yes. And following that, the connection to this EC2 instance is now established. Just as we did previously, there are a few prerequisites which you'll need to set up. So I won't explain each of these in detail. We will need to run a yum update -y. And once that is done, we will need to run a yum install for Telnet. So once Telnet is installed, we proceed over to the next installation. And this is to install Emacs. And once Emacs is ready, we will need to install Docker. Docker, of course, will be needed in order for us to run the CLI container. Following the installation of Docker, we will need to start the Docker service so that the Docker container engine will be running on this node. So for that, we execute sudo service docker start. Now that the Docker daemon is up and running, we will ensure that we are able to run Docker commands without having to type sudo before it each time by adding this ec2-user to the Docker group. With Docker now set up, we will need to download and then install Docker Compose. So we download the Docker Compose binary for this OS, and this will be downloaded to /user/local/bin/Docker Compose. Once that is complete, we will need to ensure that execute permissions are available for Docker Compose. So we run this chmod command granting execute privileges to all users. And the next thing for us is to install libtool. So we use yum for that once more. And once that is done, it is time for us to install Golang. So we download the Golang package using wget. And once that is done, we will need to unpack this archive. So we confirm first that this gzip file has been downloaded. And then following that, we unpack it using the tar command. We will run an ls once more to confirm that a Go directory has been created, following which we move the contents of that directory to /user/local. We proceed with the tool installation now, this time for libtool-ltdl-dlevel. Following that, we will need to install git, and this of course will be needed for us to download the source code for our chain code. So once git has been set up, it is time to add a few entries to the bash profile file. So I'm now going to edit it using the nano text editor. So there is a bare bones bash profile already here. And I'm now going to include a few environment variables, which includes a go root, a go path, and then the path environment variable will be configured to include the Golang binaries and also the Fabric CA binaries, which we are yet to download. So with that done, we can go ahead and save the bash profile. And then for the changes to take effect, we run source bash profile. So with the setup complete, let us quickly do a check that the tools have been set up correctly. So we can check the version of Docker by running sudo docker version. So it's 18.06 in my case. We then check the version for Docker Compose, and we had explicitly downloaded version 1.20, which is what has been installed here. And then we can check the version for Go. And for Golang, the version is 1.10.3. All right, it is now time for us to check the version of the AWS binary, and this is version 1.16.102, and this may not be the latest version of AWS. Just to be sure, we will be downloading the latest version in just a little bit. But before that, we can check where exactly this binary is now available. And this is in the user bin directory. And I'm now going to cd into that directory and remove the AWS binary, which is currently set up. Heading back to the home directory, the next thing to do is to download pip. So for this, I'm going to make use of curl to download this getpip.py script. And then following that, we can execute it in order to get the latest version of pip. So once this is run, the latest version of pip will be available for the current user, following which we can install the AWS package. So here we run a pip install AWS with the upgrade flag so that it will be upgraded if it is available already. But of course, that does not apply to us since we deleted the AWS package previously. So we can now install the AWS CLI package. So once again, we make use of pip for that. And once that is complete, it is time to check the installation of the AWS binary. So we run which AWS, and this is now available in the home directory within a directory called .local. So this is different from the /user/bin directory where it was available previously. And just to make sure that this does work as expected, we just run AWS from the command line. And when we do that, we do get an output which confirms that this AWS binary is available via the path environment variable. So at this point, all of the installation is complete for this client instance, and we can go ahead and configure it to work with the Hyperledger Fabric network. We have installed all of the tools which we require to set up this EC2 instance as a client for org2 on our Hyperledger Fabric network. This involved the setting up of Docker, Docker Compose, Golang, and also the AWS client. It is now time to configure the AWS CLI in order to work with the credentials of the user we had created previously. So we run the command AWS configure for that, and we are prompted to enter the details of the AWS access key for the user. The details of this access key are available in this credentials.csv file, which we had downloaded. So we can open that, copy over the AWS access key ID, and then heading back to the shell, we paste it here, following which we will be prompted to enter the AWS secret access key. We head back to the credentials file and then paste that detail over here as well. And then there are these two optional fields for the region and the default output format, which we can leave as blank. It is at this time where we can get the details of the CA endpoint for org2 in our Fabric network. To do this, we need to run the command AWS manage blockchain get member, and this command will return all of the details related to one of the members on our network. The arguments to this command include the network whose members' details we wish to receive. So in this case, we have supplied the ID of our Fabric network. This is the one which begins with N-G5LH. Following that, we need to specify the member of that network whose details we wish to retrieve. And for the org2 member, in my case, this is an ID which begins with M-XP7. So to retrieve that detail, I'm now going to head back to the AWS console, close this out, and then navigate it over to the AWS Manage Blockchain service. So the Fabric network ID is available here. And then in order to get the details of the individual members, we click this link, head over to the members page, and then the details of org2, including the member ID, is available right here. So now we know how to create this AWS Manage Blockchain Get Member command. And when we run this, we are returned all of the details of this org2 member, which includes the admin username as well as the CA endpoint for the certificate authority for this organization. So just keep an eye out on this full CA endpoint here. And then as a sanity check, we will ensure this is the same detail which is available via the AWS console. So we head back to the console now, and then clicking on org2, the details section includes this same Fabric Certificate Authority endpoint. So this setup looks good, but we do need to ensure that this is in fact reachable. So for that, we can copy this endpoint, and then heading back to the shell of our EC2 instance, we use Telnet now in order to hit that endpoint. And with Telnet, we need to separate out the host name and the port number with a space. And with that done, the connection to our CA endpoint is a success. So we now know that has been set up correctly. So we can get out of this Telnet connection. And then following that, we will need to download the Fabric CA binaries from its GitHub repo. So here we make use of the go get command for that. And once the download is complete, we can cd into the directory where this should be downloaded. And then from there, we will run the command git fetch. This will receive all of the new files, following which we will switch over to the branch release-1.2. So this version, of course, matches the one for our Hyperledger Fabric framework. And then once we have all the sources on our local file system, it is time for us to create a binary by building the sources. So we execute the make file for this project by running make fabric-ca-client. And now our Fabric client binary has been set up. At this point, we can download the source code of the smart contract which we had seen previously. So we can make it available on this EC2 instance as well. And though I'm downloading it from a Git repo, this file is also available in the course materials, and you can simply copy over its contents from there. However, once the code has been downloaded, we can just ensure that this car store directory is available here containing the source code, because when we next create the CLI container, we will be making sure that this source code directory is available within the container as well. So at this point, let us edit this docker compose cli.yaml file. And in here, we set up the CLI container, which includes a number of different definitions, including the environment variables. And in the volume section, you can see exactly the mapping of our source code directory to /opt/gopath/source/github.com in the CLI container. So it is within the gopath/source directory there. With the docker compose YAML setup, we can save this file. And then in order to bring up the CLI container, we will need to run the docker compose up command. So this compose cli.yaml file is provided as an argument here. With that done, our CLI container should be up and running, and we can confirm that by running docker ps. And yes, the CLI container is indeed available. It is at this point where we begin setting up the admin user for this second organization, for which we need to make use of this admin user's certificate. Now, for the purposes of this demo, I'm just going to reuse the same certificate which we had used previously for org1, and this is something which can be downloaded from an S3 bucket which has been supplied by AWS for specifically demo purposes. So we can copy this down to our EC2 instance by running the command aws s3 cp. So this is the manage blockchain-tls-chain.pem file which we're downloading here. And once that is done, we can make use of OpenSSL in order to view the contents of the certificate in a more human readable format. With this certificate ready though, it is time for us to enroll this identity represented by the certificate as an admin on this Fabric CA. For that, we can run the command Fabric CA client enroll, followed by the URL for the Fabric CA endpoint. And in here, we include the credentials for the admin for org2. And following that, we specify within the tls.certfiles argument this particular certificate. The MSP directory is also listed here. And then once this is done, we have enrolled an admin for org2. And while we have this certificate filed in this local directory, when we view the contents of the admin-msp directory, we see the certificate in the signed search directory, but we need to make it available in the admin search directory, which we can do by effectively replicating the signed search directory and calling this copy admin search. And then when we view the contents of admin-msp once more, we see that this admin search directory now includes our newly downloaded certificate as an admin. It's at this point where we head back to our AWS console, and once we're within the org2 view, we can go ahead and create a new peer node which will be added to our network. So we click to create a new peer node, and then we select a blockchain instance type, and I'm just going to select one which is the bc.t3.small, and then choose one of the available availability zones. And then once this peer is created, we have joined a new peer for org2 to the Hyperledger Fabric network. The next step for us is to create a channel which includes the peers on both of the organizations which we have set up so far, and then use both of them in order to record transactions on the blockchain. At this point, we have a Hyperledger Fabric network set up, which includes two organizations. Each of these orgs has one peer on them. However, there is no channel set up yet which connects both of those peers, which allows them to both interact with each other and record transactions on the network. For this to happen, a few steps need to be carried out, and this includes the addition of org2's administrator certificate as well as org2's root CA certificate over to org1, which is the network creator. We will do this and the remaining steps in order to set up a joint channel, and I'm starting off in the AWS Manage Blockchain dashboard for org1. So the details of the network are visible here, and we can quickly confirm what is available in the network. Heading over to members, we can see that org1 is part of the network, as is org2. We will now need to connect to org1's EC2 instance, for which we head over to Services and then to EC2. And then from the dashboard, we click on Running Instances. And then selecting our EC2 instance, we will click the button to connect. From here, we can copy over this SSH command, and then heading over to the shell, we can establish a connection to that EC2 instance. Now, this is just in case you do not already have that instance running. So with this, our SSH connection to that EC2 instance has been set up, and it is from here where we will now proceed to add the administrator certificate for org2 to the admin search directory for this org1. Now, the way to do this is we will need to create a directory to represent the org2 MSP. So I'm creating one within this home directory for this user, and this is called org2-msp. And we will then create a subdirectory within that called admin search, where the admin certificate for org2 will be placed. We will also create a directory called CA search, following which we will cd into the admin search directory. Now, this is where we will need to copy over the administrator certificate for org2. And in a realistic scenario, this certificate will be handed over securely in some manner. But for the purposes of our demo, I'm now going to bring up the other terminal in which I'm connected to the EC2 instance for org2. The certificate for org2's admin is available within the admin-msp directory. So I'm now going to view the contents of this certificate here, copy over the contents, And then switching back to org1, we can create a new cert.pem file within the admin certs directory and then paste the contents within this file. So just to recap where we are currently on org1's EC2 instance, and we have created a directory for org2's MSP, and within that we have created an admin certs subdirectory within which we have copied over the contents of the org2 admin's certificate. With that done, we can now head back to the org2's EC2 instance, because the next step for us is to copy over the certificate for org2's root CA over to org1. So this root CA file is available within this CA certs directory. And I'm now once again going to copy the contents of this CA certs file over to org1's EC2 instance. So we can open up this file, copy its contents. So this is still on org2. We switch over to the shell of org1's EC2 instance, and I have now cd'd into the CA certs directory there. So we were previously in the admin certs directory on the org1 instance, and we are now in the CA certs directory for the org2-MSP directory. And within that, we will create another PEM file to mirror the one which is available on org2. And here, we will paste the contents of that CA file for org2 right here. So at this point, we can quickly recap what we have just done. Within the org1's EC2 instance, we created a directory called org2-MSP within its home directory. And this is a directory which is meant to store all of the certificates related to org2. Within that directory, we created two subdirectories called admin certs and CA certs. Within the admin certs directory, we copied over the administrative certificate for org2. And then within the CA certs directory, we copied over the certificate for org2's root CA. At this point, all of the certificates for the different organizations in the Hyperledger Fabric network are available in this EC2 instance for org1. We will use this fact in order to set up a new channel which includes both org1 and org2, and that will happen in the next video. I'm now connected to the EC2 instance, which serves as the client for org1 in our Fabric network. In the previous video, we copied over both the administrative user certificate for org2 as well as org2's root CA certificate over to this EC2 instance. Given that this host also contains all of the certificates related to org1, we can use the availability of all of these digital identities in order to set up a new channel involving both org1 and org2. Before we proceed, we can run one command in order to view all of the members of our Hyperledger Fabric network at this point. The specific command to execute is AWS managed blockchain list-members. The arguments to this include the ID of the network whose members we wish to view, and then we can also specify the region over here, which I'm specifying as US East 1. When running this, all of the members will be returned in a JSON format. And first, I'm getting the details for org2, which is now well and truly part of this Fabric network. And then, once the page refreshes a little bit, the details for org1 also show up. You can see from the status that both of these members are now available. So now that our Fabric network includes two different organizations, what does the channel definition contain? For this, we can open up the configstx.yaml file, and when we look into it, we observe that there is just a single channel which includes just one organization, specifically org1. Now, the purpose of having two organizations in our network is for them to be able to communicate along a secure channel, and it is now up to us to provision this channel. The way to do that is to modify this configstx.yaml file so that in the profile definition, we specify a second org in the organizations block. At the moment, there is just this reference to the org1 definition which we can find further up in the page. So the modification which we need to perform to this file must include the addition of another organization definition, which mirrors this block for org1 but contains the identities for org2. So now I'm going to exit out of this file, and then we'll go ahead and delete the configstx.yaml file. Following that, I'll re-edit it and then paste the contents of the new file. And in this case, you will see that in the profile section at the bottom, a couple of changes have been made. Firstly, the name of this channel profile has changed from one org channel to two org channel. And then under the organizations block, there is not just org1, but we also have a reference to a block for org2. Now the actual definition of this org2 block will be further up in the file. So when we head to the top, under the organizations block, we not only have org1 defined here, but we also have the details for org2. We not only include the name and the ID for this organization member, but for the MSP directory field, we assign to it the directory which includes the certificates which we copied over for organization 2. With these changes made to the configstx.yaml file, we now have a definition for a channel which represents both of the organizations in our fabric network. We can now save the changes to this new version of the configstx.yaml file, and then following that, we can use this file in order to create the channel creation transaction file for this new channel which we have defined. The way to do that is to make use of the configstx.gen binary which is available in the CLI container, and the way to run that is by means of the docker exec command. So we run docker exec CLI configstx.gen, and then we pass along the different arguments to that. We mentioned that the channel creation transaction details must be output to a file called rchannel.pb in the home directory, and then the profile out of which this channel will be built is the one called 2org channel defined within the configstx.yaml file. The channel ID for our new channel is rchannel, while the config path argument specifies where the configstx.yaml file can be found, which is the home directory for this user. When we execute this command, the channel creation transaction file should be generated, and the next step for us is to go ahead and actually create the channel, for which we will run the pure channel create command from the CLI container, and we will pass along all of the environment variables related to the first peer for org1 in our network. We also mentioned that the name of the channel to be created is rchannel, and it will be created out of the transaction defined in rchannel.pb. And when we run this new channel containing both of our organizations called rchannel will be created. At this point, we can run an ls from this directory. From here, we can confirm that this file called rchannel.pb was created earlier on. And now that we have this 2org channel, we should set it up in such a way that either of the organizations can use their clients in order to invoke transactions which get stored on the blockchain for that channel. For that, we need to make some changes to the org2 client. So I'm now switching over the shell, and I'm now in the EC2 instance for org2. From the home directory, I'm just running an ls, and this of course has a different set of files than what we did in org1. But in order to be able to use this as a client, we need to make a few changes to the bash profile. So editing that using the nano text editor, I'll go ahead and add a couple of environment variables, starting with the MSP path directory. And then we'll also set the MSP environment variable, which includes the ID for this organization. You should be familiar with how this value can be obtained from the AWS dashboard. Next, we will need to specify the location of the orderer service. And this is something which you can get from the details of the network from the AWS dashboard. And this is the ordering service endpoint, which is the same for both org1 and org2. So now that we have specified the orderer, the next is for us to specify the peer endpoint which this client will need to connect to. In case you're not sure where this peer endpoint comes from, we can head over to the AWS dashboard, over to the member section of the network, and then click on org2. At the bottom, the different peers for org2 will be listed, and you can click on the single peer we instantiated. And this is where that peer endpoint can be obtained. So with these 4 environment variables set, our bash profile changes can be saved. And then for it to take effect, we run the source command. So with those environment variables set, it is possible for us to run peer commands from this client in order to communicate with the Fabric network. So while we created the to-org channel on the peer for org1, this channel has not been set up on org2's peer just yet. We can do that by running the peer channel fetch command, and once again by means of docker exec. And in order for this command to reference the org2 peer, we pass along the environment variables which we just defined in the bash profile. The peer channel fetch command will fetch the specified block from the blockchain for the channel over to the peer for org2. In this particular instance, we are telling the command to fetch the oldest block for the channel, which will be written to a file called rchannel.block in the home directory. So this will fetch the Genesis block for our newly created channel. And when we run this command, the Genesis block of our newly created channel called rchannel will be downloaded from the Fabric network, and the Genesis block will be available in a file called rchannel.block locally. And with that, we can now join this second peer for org2 over to this channel using that Genesis block. So we run the command peer channel join, and then we specify as an argument this newly downloaded Genesis block. So when we run this, org2 is now part of this channel called rchannel. I have now switched over to the shell of the client instance for org1. And from here, we will run a similar command as we did previously for peer channel fetch in order for the Genesis block to be fetched into this host. And then with that done, we can run the peer channel join command from org1's instance as well. And with both of these commands executed, we now have both of the organization's peers as members of our newly created to-org channel. It is now time for us to install the CarStore chain code onto both of the peers in this channel, and then we can test the channel by invoking transactions from each of those peers. In order to deploy the chain code, I'm now switching back to the shell of the second organization, and then from here we'll run the command peer chain code install, and this is again through the CLI container, and we will need to specify the name of the chain code, which is mycc, followed by the version, which is v0, and then within the CLI container, this chain code can be found within the location github.com/go, which is a path that is relative to the go path/source directory on that container. The environment variables which we pass along will ensure that the peer commands are run in the context of the peer in org2. Just as a reminder, the installation of chain code needs to happen on each of the peers which need access to that chain code. It is the instantiation of chain code which happens per channel. So when we run this, the peer in org2 now has the chain code installed. I will now switch shells once more over to the EC2 instance which serves as the client for org1. And one thing to keep in mind at this point is that we don't need to run the same peer chain code install command for the peer on org1 on this occasion. The reason is that we have already installed the same chain code to that peer, even though that chain code was instantiated on the other channel which had just the one organization in it. So at this point, both of the peer nodes on org1 and org2 have the same chain code which is referenced as mycc, and version 0 of that installed. So what we can do from this client for org1 is to instantiate the chain code on the new to.org channel. So from the point of view of org1, the chain code will be installed just once, but will be instantiated on two different channels it happens to be part of. Now let us examine this pure chain code instantiate command. Since we are running it through the CLI container, we pass along the environment variables so that it runs in the context of the peer for org1. And then we have the pure chain code instantiate command, whose arguments include the channel on which this chain code is being instantiated. And this is the to.org channel called R channel. We then specify the name and version of the chain code, which is mycc and v0. And then there are no arguments to be passed to the init method of the chain code, which is why we leave the args field as a blank array. Now at the end, in addition to passing along the CA file, we also make use of the -P option, which is meant to specify the endorsement policy for this chain code. Here we use the AND keyword followed by parentheses, within which we list down both of the members which make up our channel. This means that any transactions originating from this chain code need to be endorsed by both of these members in order for that transactions to be validated. So now with our pure chain code instantiate command set, which includes an endorsement policy, we can go ahead and run this command. And at this point, the chain code has been deployed to our newly created to.org channel on the Fabric network. In the next video, we will invoke transactions from the client for both of the organizations to confirm that both of them are able to record transactions on their shared blockchain. With the chain code now deployed to both of the peers which make up the Hyperledger Fabric network, and the fact that it is now instantiated on the channel containing both of the organizations, it is now time for us to invoke transactions on that chain code, and we will be doing this using the clients for each of the organizations on this channel. One thing to keep in mind is that when we instantiated the channel, we set an endorsement policy for the chain code which specified that endorsements need to be obtained from both of the members who are connected to that channel in order for the transaction to be validated. This means that when we submit transactions using that chain code, we will need to specify both of the peer endpoints. As a quick refresher on how these endpoints can be obtained, I'm now in the dashboard for the second organization. I head over to org2 and then to the section for peer nodes, and then clicking on this peer for org2, the peer endpoint is available right here. And the interface allows us to copy this value as well by means of this button. We will next be submitting a transaction on the channel, and we will need to specify this peer endpoint. I'm now switching over to the shell of the EC2 instance, which is the client for org1 in our channel. The transaction I'm going to submit here is an invocation of the Init Ledger method defined in our chain code. And for that, we run the pure chain code invoke command. We specify the name of the channel and the chain code, followed by the arguments which need to be passed to the invoke method in the chain code. This includes the name of the function to be triggered, which is Init Ledger, followed by the arguments to that function, and this does not take in any arguments. And then following that, you will notice that we make use of this peer address argument, not once, but twice. This is because we are submitting this transaction to both of the peers in our channel, and we specify the peer address by means of the peer endpoint. Since we are running this from the org1 EC2 instance, the address of org1's peer is available in the peer environment variable, which we set in the bash profile. And then the peer endpoint for org2 is the one we just copied over from the EC2 dashboard. In addition to the peer endpoints, we also have two occurrences of the TLS root cert files argument. And this is where we pass along the TLS root certificate files of each of the peers, and in our specific example, we happen to use the exact same certificate for each of the peers. In a real setting, however, you will have different certificates, in which case the certificate which is passed along in this argument needs to correspond to the peer address which is specified immediately preceding it. And then we finish off this command by specifying the orderer node, followed by a trusted certificate for the ordering endpoint. And now, when we run this command, our peer chain code invoke operation seems to have taken place successfully. And there is, of course, one way to confirm this, where we can now query our chain code. So we run the command peer chain code query. And since this does not involve the submission of a transaction, we don't need to specify the peer addresses this time. So we only pass along in the arguments the name of the channel, the chain code, followed by the function which needs to be invoked and its arguments. And when we execute this, all of the 10 vehicles which are loaded into the state of the contract by a call to Init Ledger are now available here. So the submission of a transaction was indeed a success. And we have also confirmed that we're able to query our chain code. We will now go ahead and invoke one more transaction. So the structure of this peer chain code invoke command is going to be similar to what we had previously, which includes the submission of the transaction to both of the peers, except on this occasion, the function in our chain code which we're triggering is the one called createCar. And this, of course, expects 5 different arguments which we pass along in this args field. This includes the ID of the car which needs to be added to the state, followed by the details for the car. So this is a black Tesla Model S, which is going to be owned by Bob. Of course, this is followed up by specifying the peer addresses, followed by their respective TLS root cert files, and then with the orderer mentioned at the end. And now when we run this command, we get a successful status message returned. So while we have successfully made updates to the contract state, the true test for us is to make sure that these state changes are visible to org2 as well. So for that, I'm now going to switch over the shell and then head over to the client for org2. And then from here, we'll run a peer chain code query command to see if the updates made to the contract state from org1 are available to org2. And when we run this, we get a large JSON output. And then to confirm that car 10 has indeed been added, we may need to search a little bit, but we have this confirmation. So we have now successfully recorded transactions on this smart contract from org1, and this included the invocation of the Init Ledger method and the createCar method, and we have been able to view all of those changes from org2. This is confirmation of the fact that we really do have a shared channel between the two organizations in our Fabric network. We have now covered the scenario where it is org1 which invokes the transactions and org2 reads from the chain code in order to view the updates made to the contract state as a result of those transactions. We will now test out the other scenario where it is org2 which invokes the transactions. To do this, org2 will need to know the endpoint for the peer on org1 because it will be submitting its transactions to both of the peers. And to do this, I'm now in the dashboard for org1. And to get the details of the peer endpoint, I first click on this org1 link. This, of course, includes information about the org itself, including the Fabric CA endpoint. But what we are interested in is the peer endpoint. So we click on this peer node link and then capture the peer endpoint right here. So we can assume that someone from org1 has copied this over and then sent it to org2. And then from the client for org2, we run a peer chain code invoke command. And this is a call to the createCar function, which involves the addition of a Peugeot 205, which is purple in color, as car 11 in the contract state. The transaction which this will create needs to be submitted to both of the peers on the channel, and the address of the peer for org2 is available in the peer environment variable, And with this second peer address argument, we list the peer endpoint for org1. And when we run this transaction submission seems to have gone through successfully. And of course, to confirm this, we invoke the query all cars function from here. And the results confirm that car 11, which is the new Peugeot 205, has indeed been added to the contract state. Now that we have successfully submitted a transaction from org2's client, it is now time to confirm that org1 is able to view the changes to the same contract state. So heading over to the client for org1, we can call the query all cars function from here. And then we hope to see the details for car 11, which has just been added by org2. And when we search through the results which are returned, we can confirm that the update made to the contract state by org2 is also available to org1. So we have now successfully set up a multi-org channel on a Hyperledger Fabric network which spans 2 AWS accounts. And that concludes this demo on AWS Managed Blockchain. With that, we can just make sure that we exit out of these shells. So I'm disconnecting from each of the shells which I'm connected to. And as a cleanup, you can also go ahead and delete the AWS Managed Blockchain network. And that is something which can be done when each of the organizations which are connected to the network withdraw their membership. In this exercise, you will start off by describing proposals in AWS Managed Blockchain. During this course, we did create a proposal, and you will need to recollect exactly what purpose a proposal serves and the exact steps which need to be followed in order for a proposal to be approved. Next, you will recollect the steps involved in deploying chain code on a channel in Hyperledger Fabric. We saw during the labs of this course that deploying chain code is not a single step process and in fact requires 2 different commands to be executed. You will need to recall exactly what those are and what purpose each of them serves. Since both of these topics were covered during this course, you may pause this video and then take some time to perform each of the tasks on your own. For the first task, you needed to describe proposals in the context of AWS Managed Blockchain. A proposal is created in order to change the membership of an existing blockchain network. That is, to either add or remove members from the blockchain network. A proposal can be raised by any of the existing members of the network, and one form of proposal is to extend an invitation to one or more AWS accounts to the blockchain network. Alternatively, proposals can also be raised in order to initiate the process of removing one of the existing members of the network. The raising of a proposal is, however, just the first step towards changing the membership of the blockchain network, since they are subject to a voting policy before the invitation is extended to a new member or one of the existing members is removed. A voting policy is one which is defined at the level of the network rather than at the level of the proposal. The voting policy is defined in terms of a certain percentage of the existing members who must approve of the proposal. Once this stipulated percentage has been matched or exceeded, then the proposal is considered approved, but only if all of the yes votes come in before the expiration of the proposal. So this is another detail in the voting policy where an expiration period is defined for a proposal, and this ranges from a minimum of 1 hour to a maximum of 1 week. So if a proposal gets the required number of yes votes before it expires, then that proposal is considered approved and an invitation is either extended to a new member or one of the existing members is removed from the network. In the case where the proposal involves extending an invitation, adding that new member to the network not only requires the approval of the proposal, but is also subject to the invitee accepting the invitation. Moving on to the next task, you needed to recall the different steps involved in deploying chain code to a channel on a Hyperledger fabric network. So deploying chain code involves two different steps. First of all, the contract needs to be installed on each of the peers which need access to the contract. And this is done by means of the peer chain code install command if you happen to be using the Hyperledger Fabric CLI. An installed chain code is referred to by its name and version, and it is possible for you to update your existing chain code and then reinstall it by just using the same name and a different version number. The peers on your network on which the chain code needs to be installed include those which wish to submit transactions, as well as those which need to endorse the transactions as well. So when installing chain code, you will need to make sure that enough peers have the chain code installed in order to fulfill the endorsement policy which has been set for it. So the first step here is to install the chain code on individual peers in the network. The next step in the deployment, though, is to instantiate the chain code, and this happens at the level of channels rather than peers. We saw during the course that it is possible to have chain code installed just once on a particular peer, but then instantiated multiple times if that peer happens to be part of multiple channels which use that chain code. The command to execute if you're using the CLI is peer chain code instantiate, and running this command will invoke a call to the init method defined within your chain code. Since init effectively serves as a constructor, if this method happens to accept arguments, you will pass those along with your peer chain code instantiate command. So to summarize, deploying chain code in a Hyperledger Fabric network involves two different steps. The first of these is to install the chain code on individual peers, and the next is to instantiate the chain code at the level of channels. In this course, we will be setting up a blockchain network on the cloud using Microsoft Azure's Blockchain Workbench. This course will require you to have an account on Microsoft's Azure service, and if you don't, you can go ahead and create the account and then come back to this video once you have that set up. The first thing we're going to do here is to bring up a browser window and then navigate to azure.microsoft.com. This will take us to the Azure homepage, where you can view some of the high-level details of the features which are offered on Azure. However, what we are interested in is to set up a blockchain network using the Azure Blockchain Workbench, for which we need to connect to the Azure portal. So you can just click on this link to the portal in the top right. And in my case, since I was already signed in to my Azure account, I am taken directly to the dashboard. You may need to enter your credentials if you're not signed in already, but once you're in this dashboard, the first thing we will do is to navigate in the menu on the left and then create a new resource group. A resource group on Azure can be thought of as a logical grouping of all of the resources associated with a specific project. So when we click on resource groups over here, if you're already familiar with Azure and you have used it before, you may already have a few resource groups set up, which is the case with my account. But in order to use the Azure Blockchain Workbench service, we will need to create a brand new resource group. For that, we navigate to the top and hit Add. And following that, some details will need to be entered for the resource group. You may need to map this resource group to a specific subscription which you have set up in your Azure account. And then following that, you will need to enter the name for the resource group. I'm going to call this Blockchain RG to specify that it's a blockchain resource group. And I'll have this resource group created within the US Central region. And following that, we can just go ahead and click the button to review plus create. Here we can quickly verify that the details which we have entered are correct. And then if they look fine, we just hit create. And within a minute or two, you may see that this resource group has been set up and a notification should appear in the top right. Since I have fast forwarded, this has popped up immediately and I'm just going to close this. And to view the new resource group in this resource groups page, we may just need to hit the refresh button. And yes, the blockchain resource group does indeed pop up here. To view the details for the resource group, we can just click on this. And as you would expect, there are no resources created here just yet, which is why this list is empty. But we will be fixing that now by provisioning some resources using the Azure Blockchain Workbench. To make use of this service, we can go over to this search bar over here, and we will navigate to the Azure Marketplace, because that is where we will find this service. And once we get to the marketplace, there are a number of different options, but the menu on the left provides some kind of categorization. And what we are interested in is right at the bottom, at least at the time of this recording for me, which is blockchain. Clicking on blockchain, once again, there are a number of different options available. In order to search for the Azure Blockchain Workbench, however, we make use of the search bar and then just type in Azure Blockchain. And out of the options available, I will select the Blockchain Workbench. With that done, we will be taken over to the page from which we can create this Azure Blockchain Workbench resource. And the different details for this particular service are available right here. For example, you can see here that the Blockchain Workbench actually comprises a number of other Azure services, which includes a SQL database, a storage account, and so on. And then scrolling further down, there are also a number of links available for the service, but we won't really be looking at that, and we'll just scroll right to the top and then choose to create a new blockchain workbench. We will now need to enter some details for this workbench, starting with the basic section, where we will be prompted to enter some kind of prefix which will be used for the different resources under the blockchain workbench. And since we will be setting up this blockchain network in order to deploy an application which will allow the transfer of assets, the prefix which I'm going to set here is asset transfer. The workbench will provision a VM instance as well, and the username for that I'm going to set as asset transfer VM. As for the authentication types, we can choose between having a password to go with the username, or we can set up an SSH key. And if we choose the second option, we will be prompted to enter some additional details. I will stick with the password, however. And then following that, we'll need to enter the password and then confirm that as well. Following that, we will need to set up a database and blockchain password. So this is separate from the blockchain workbench password here. So if you're using separate passwords, do make note of each of those. The next thing to do is to specify the deployment region, which I'm going to select as US East. And then the subscription, which will be used for this, is the one which I have called Pay As You Go. The next thing to do is to assign this particular blockchain workbench to one of the existing resource groups. Note here that this must be assigned to an empty resource group, which is why I'm selecting the blockchain RG one, which was just provisioned. With that selection made, you will finally be prompted to enter a location, which I'm going to leave as US Central. This is the location where all of the blockchain metadata will be stored. With these details set in, we can hit OK, which will validate the details which you have entered, and then take you along to the advanced settings. From here, there are a few advanced configurations which are possible. For example, you can choose to create a brand new blockchain network or use an existing one. And if you choose the latter option, you will be prompted to enter the Vpc endpoint for that. But in our case, we just want to create a new network, which is why I'm choosing that option. And then following that, we can also choose the specific pricing tier which we want. And I'm going to leave this as basic. And we can also control membership to this blockchain network by means of Azure Active Directory, which can be configured right now, but I'll choose to add that later on. We can also configure the VM instance which will be set up, and I'm going to leave this as the default again and just hit OK. This takes us along now to the summary, where the details which we have entered in the previous forms will be published, and we just need to confirm that everything looks good. A validation will also be occurring at this point. And once everything checks out, we can just go ahead and hit OK. And this is the point at which you will need to confirm that you wish to purchase this Azure Blockchain Workbench service. So I'm just going to quickly fast forward with this terms of use and then hit create. Now setting this up could take a few minutes. So I'm just going to close down this notification which pops up. Some notifications will pop up here and you can click on this link in order to view what they are. And you can track the provisioning of this blockchain workbench right here. So clicking on this will show you the different resources which have already been provisioned as part of the workbench. And I'm just going to fast forward this. You can track each resource as they get set up and continuing to fast forward until about 30 minutes later when all of the resources for this blockchain workbench have been set up. Now that we have deployed an instance of the Azure Blockchain Workbench, I'll just talk a little about the application which we will be creating on it. The application will enable the transfer of assets between different employees working in the same organization. The specific asset we will use in our example will be a company car, and this is an asset which will first be assigned to one of the employees, and once they're done using it, they can mark that car as available, in which case some of the other employees can put in a request for the vehicle. Once the request is approved, then that asset will be transferred over to the one making the request. And to showcase this functionality, we will be creating multiple users who can access the application and will represent the employees between whom the car is being transferred. Before we get into that now, let us take a look at the resource group which we have set up. So we click on resource groups and then click on the blockchain RG which we just created. And since the Azure Workbench is the only one which is deployed to this resource group, we can see that there are in fact 22 different deployments which were involved in setting it up. As for the individual Azure resources which make up the Workbench, we can scroll down and take a look at each of these right here. For example, there is a public IP address, there is a SQL server, as well as a VM instance. So the blockchain workbench is essentially an umbrella of Azure Services. Now, I had mentioned just a little earlier that there will be multiple employees who will be able to access the application we will soon deploy. And these employees will need to connect to the blockchain network using their company email accounts. In order to enable that, we will need to set up these users in the Azure Active Directory. So this is what we will navigate to right now. When we get to this dashboard, we observe that there is a default directory which has automatically been created. And in the case of the account I'm logged in as, which is cloud.user@lunicorn.com, a domain clouduserlunicorn.onmicrosoft.com has been created automatically. You may see something similar depending on the user you are logged in as, but whatever domain you see here, you can make use of that when adding new users to the Azure Active Directory. Now, to add additional users, we can navigate in the menu on the left to the users view. And in my case, I haven't added any new users, which is why just the user I'm currently logged in as is visible here. Let us go ahead and set up some new users now by clicking on the new user button. We will then need to fill up this form, which includes details of the name of the user. So the one I'm going to create is Alice. And in the place of the username, we can specify the user's email address. So within my organization, I've created an email account called alice@lunicorn.com. And I'm able to do this because I have added my organization's lunicorn.com domain as a verified domain in my Azure account. If your organization's domain has not been set up in your account yet, then you can make use of the auto-generated domain. In my case, it is clouduserlunicorn.onmicrosoft.com, and you will need to make use of the equivalent for your account. In any case, this username which you specify must be some string followed by the @ symbol, followed by a domain. And then following that, we can specify a profile for this user. So here I'm going to enter the first and last name of Alice, and you can also add in some work-related info if needed. I'll just skip that though, and then head over to the properties section. It is likely that you won't be able to edit this particular field, and we don't really need this for our blockchain workbench setup, so we can skip it. Heading over to groups. If you have any group set up in your Azure Active Directory, you can specify which group this user will belong to, but I don't have any set up just yet, so I'll just proceed to the next step. And this is where you can specify what role this user will play in the Active Directory. So the options are user, global administrator, and limited administrator. And the list of permissions associated with each of those are visible in the list below. Now you can choose whichever option suits your purpose. But in my case, I'm just going to scroll all the way to the top and leave Alice as a regular user, which was the default setting in any case. So I can just close out of this since I haven't made any changes. And now we can view the password which Azure has created for this user by checking this box. And then you can make note of this password because for this demo, we will be logging in as Alice a few times. So once this has been copied over, I'm going to paste it into some text file. And then I will keep referring to this when I have to log in as Alice. We will be creating a few additional users, and you can make use of the same text file in order to store all of the passwords. Switching back now to the Azure portal, we can just go ahead and click Create so that Alice will be a new user in the Azure Active Directory. So with one user created, we can go ahead and create a couple more. So I'll just close this notification and then click New User for a second time. And this second user we are provisioning is going to be called Bob. I also have an email account called bob@lunicorn.com set up. And once again, you will need to make use of a verified domain. And if not, you can make use of the auto-generated one for Active Directory. I won't provide any of the other details, but will just show the password for this Bob user and then copy it down and then store it in the text file which I had set up. So with two passwords saved, we can head back to the portal and then hit Create. And in a few seconds, we will now have created both Alice and Bob as users on our Active Directory. I'm also going to create a third user now. So once again, we'll go ahead and click New User. And the name of this third user is going to be Charles. Again, there is an account called charles@lunicorn.com. We'll display the password for this user, store it in the text file, and then head back to the portal and hit Create. All right, that is all the users which we need for this demo. So we now have 3 different users set up on Active Directory, and we can use them all later on in order to interact with our asset transfer application. Now, the Azure Blockchain Workbench comes with a UI from which we can load the details of our smart contract along with a config file which includes different workflows for our application. It is now time for us to access that Workbench UI. So I'll just go ahead and close this notification and then head over to resource groups. We will need to go to the blockchain RG resource group which we created. And then out of all of the different resources listed here, we'll need to scroll down to the one which falls into the type of app service. It is these app services which represent the application from which we can upload the smart contract and config file and then interact with that application. Now there are 2 different app services here. One of them is for the API service, and we don't really need to use that directly. So we click on this other app service, and when the details of that get populated here, we can access that app service by means of the URL which is available in the top right. We will bring this up and interact with it in the next video. Having provisioned the blockchain workbench, and then also setting up the users who will eventually use the application which we will create on it. It is now time for us to initialize the web application for the Azure Blockchain Workbench tool. So from this page here, we will navigate to this URL, and then clicking on it will open this up in a new tab. So the web app is not yet initialized, and to do that, we have been provided with a few instructions. First of all, we'll have to run the specific command from a Cloud Shell instance. So first, we can copy this command over and then launch a new Cloud Shell instance by clicking this button. This has brought up a VM, and specifically, we are taken to its PowerShell. And from here, we can interact with the various services in our Azure account. Now, this provisioning might take a minute or two, but once it is done, we will have the prompt in which we can paste in the command which we copied over from the previous page. Running this will initialize the blockchain workbench UI. And you can see that this includes details such as the subscription ID and the resource group which we had set up. There is also a deployment ID right here. So we can now go ahead and run this command. At this point, we will be prompted to enter the details for an Azure Active Directory tenant. To do this, we can head back to the Azure dashboard, over to the Azure Active Directory page, and then from there, copy over this domain which has been generated for us. So it is clouduserlunicon.onmicrosoft.com for me. So I'll just copy this over and then head back to the Azure Cloud Shell and then paste this value right here. After hitting enter to proceed with the setup, we will be prompted to authenticate ourselves by navigating to this microsoft.com/device login URL and then enter this code. So I'll just click on this link and then enter the code which was given to us and hit next. And with that done, we will need to sign in as an account, and you just need to specify the credentials of your Azure account right here. Since I'm already signed into Azure with cloud.user@lunicon.com, I just click on this button, and with that done, the authentication is complete. So with that done, I'll just close out of this tab, which brings up the Azure Cloud Shell instance, and you can see that the setup has now proceeded along. Following that, you should soon see this success message, which means that the Workbench instance has been set up correctly, and we can now use its user interface in order to create our own blockchain application. So there is no more use for this Azure Cloud Shell instance, so I'll just close it down. And then beyond this, I'll just confirm that I do wish to leave this site. And now this page for the Azure Workbench will refresh. And now that the app has been set up, we will be prompted to explicitly give our permissions to this Azure Workbench app. So I'll just hit this checkbox so that the permissions will be granted, and then hit accept. And with that done, we are now logged in to the Blockchain Workbench application. Now, if you see a message such as this that the link did not work, then you can just wait to be redirected or hit refresh, in which case you will be prompted to sign into your Azure account once more. So I'll just enter my login ID followed by the password. I'll then say that I wish to stay signed in. And with that done, we are now navigated to the fully loaded home page of the Blockchain Workbench application. So within this applications view, we will be able to see the different blockchain applications which we have set up. And of course, we have not created anything just yet, which is why this page is empty. At the top right, we are told that there is just one existing member, which is the cloud.user account in my case, who is currently part of the Blockchain Workbench. Closing out of this view, we can head over to the update section of the app. And then here we can view the details of the version of the Azure Workbench which we are currently using. And we will also be notified if there are any newer versions of the app currently available. With that, we can head back to the applications page, and then we can proceed with the creation of our first blockchain application on the Azure Workbench. When we click on this button, a menu will pop up on the right of the page where you have the ability to upload the contract configuration JSON file. This configuration file, you may recall, contains all of the metadata for our blockchain application. And this is where we can define details such as the roles and workflows for the application. Now, before we upload both the config file and also the smart contract itself, we can now switch over to a text editor or an IDE, where I will walk you through both the smart contract and the config JSON file, which we will upload for this application. Both of those files I have placed in this directory called asset transfer. So I'll just expand this, and you can see both the JSON and the Solidity source file right here. We will start off by taking a look at the smart contract, which is in this Solidity file. And since all the code is here, I'll just walk you through each of the blocks one by one and then explain what exactly they accomplish. This code walkthrough will happen in the next video. It is now time to go through the Solidity source file of our asset transfer blockchain application. It is expected that you have some prior experience in Solidity programming, so I won't get into too much detail with regards to the code. We start off with the pragma directive, and here we mention that this particular source code needs to be compiled with a version of the Solidity compiler which is greater than or equal to 0.4.25 and should be less than 0.6.0. We follow that up by beginning the definition of this smart contract, and this is one called asset transfer. As touched upon earlier, this is meant to allow the transfer of an asset which belongs to an organization between different employees of that company. So we store a few different values in the fields here. We start off with an enum called state type, which represents the different states for the asset. An asset is marked as active if it has been assigned to some employee, but there is no valid request from another employee for that same asset. If someone has requested the asset, then it goes into the offer placed state, following which the person possessing the asset needs to accept the offer. When that happens, the asset goes into the pending inspection state, where some central authority will need to approve the asset transfer. And then finally, there is a terminated state where the asset is effectively rendered unusable. In addition to this state type enum, we also have an address type which represents the owner of the asset. There is an asset description, and then there is this field called state, which represents the state of the asset. This is followed up with two additional address types to represent the applicant for this particular asset and also its inspector. It is the inspector who will have to approve the transfer of an asset once both the applicant as well as its current owner are okay with the transfer. If all of this seems a little abstract, consider that there is a sales team in a company, and there are a number of salespeople who wish to use a common asset, which could be a company car. The car may initially be assigned to the salesperson Alice, who becomes the asset owner, and then following that, Bob may make a request for the asset, in which case he becomes the asset applicant. Once Bob has put in the request and Alice is okay with transferring the car over to him, this transaction needs to be approved by the asset inspector, who you could consider to be the one responsible for managing the company cars. So with the fields defined, we move over to the constructor for the smart contract. So this takes in an argument, which is a string, which describes the asset which this contract represents. So this is where you could specify, for example, the make, model, and maybe even the color of the vehicle. When initializing the car asset, it will be assigned an asset owner, and this will be the one who initializes the asset in this application. Following that, we assign the description of the asset and then set its initial state to active. So when someone initializes a car in the application, they will be made the owner of that car, and then the description for the vehicle will be set and its state will be marked as active. Following that, any further interactions of that vehicle will need to invoke the different functions we have defined within this contract. And we start off by taking a look at this terminate function. Here we run a check in order to ensure that this terminate function can only be invoked when the one invoking the function happens to be both the asset owner as well as the asset inspector. If this condition is not satisfied, then the transaction will simply be reverted. And if the condition is satisfied, then the state of this asset will be marked as terminated. Moving along now to the request function, and this is a function which someone can invoke if they wish to request possession of the asset. So with the company car example, if one of the salespeople wishes to request the car which is currently assigned to another employee, they can invoke this request function. Within the code, we first perform a check to see whether the one invoking this function is the asset owner, and if that is the case, then we will revert the transaction. We also revert the transaction if the state of the asset is not active. So if there is a pending request for this particular asset or it has been terminated, then we will revert the transaction. And finally, if the conditions are satisfied, then the person making this request is marked as the asset applicant, and the state of this asset will be marked as offer placed. Moving along now to the next function, which is called accept offer. So when an employee has made a request for a particular asset, then the person who is currently in possession of that asset needs to accept the offer. This is the first step which must be performed in order for the transfer of the asset to take place. So within the code, we first check that the asset is in the state of offer placed. So we check that an offer has indeed been placed before you can accept the offer, and if not, we revert the transaction. We will also revert the transaction if this accept offer function is being invoked by someone who is not the current owner of the asset. And if the conditions check out, then we will update the state of the asset to be pending inspection, and then we will assign an asset inspector for the asset. For the transfer of the asset to take place to the one making the offer, then this inspector will need to provide their own approval as well. It is up to the one possessing the asset to decide who this inspector needs to be. In the case of the sales team example we have been using, it could either be the head of the sales team, or it could be someone who is in charge of the vehicles which are owned by the company. And since we now have a function in order for the possessor of an asset to accept an offer, there should also be a corresponding function to reject that offer. So once again, we verify that it is the asset owner who is invoking this transaction. And if the state of the asset was offer placed, then we will update the state to active. And then we set the value of the asset applicant to effectively 0. So now that we have functions to accept and reject offers, there is one more function we need to define. And this is something which can be invoked by the one marked as the inspector of an offer. So when one employee makes a request for an asset and the one who is currently in possession of it accepts the offer, then for the ownership of the asset to actually pass over to the requester, the inspector needs to call this function. We first check whether the asset owner and the asset applicant happen to be the same person, in which case we do a revert. And if this is not the case, then we will first confirm that the state of the asset is pending inspection. And if that is the case, then we will update the state to active. We will update the asset owner so that the ownership passes over to the applicant. And then finally, we will clear the asset applicant field. And if the two conditions defined here are not met, then we will revert the transaction. So with that done, our smart contract definition is complete. It is now time for us to move on to the config file, which we will do so in the next video. In the previous video, we defined the source code for the Solidity smart contract, which will be used for our asset transfer blockchain application on the Azure Blockchain Workbench. It is now time to accompany that Solidity source file with a configuration file. This config file will include some of the application metadata as well as the roles of the different participants in the application. It will also include workflow definitions, and it is within the workflow where we can define the transition of our assets from one state to another. The reason for including such a config file is for us to be able to invoke each of the operations from the UI of the blockchain Workbench tool. And this is something which would not be possible with just a smart contract. So let us go ahead and take a look at this config file. This is, of course, in the JSON format, and we start off with some metadata. This includes the name of the application, which we will call asset transfer in camel case. And there is also a display name for the app along with a description. We then proceed with the definition of the application roles. And you'll see that for each role, there is just a name and description. These are the roles which will be assigned to the different participants in our application. And all of the employees who will be able to possess the asset and make requests for it will be users. We have also seen that the contract includes an inspector who needs to approve the transfer of an asset from one employee to another. So we have an inspector role as well. When we instantiate the application later on, we will be assigning the roles of user or inspector to the users which we provisioned earlier on in the Azure Active Directory. So with the roles defined, we can move along to the workflows for our application. So a workflow defined in this configuration file can be thought of as a collection of states and actions where the performance of a particular action causes the application to transition from one state to another. So here we have initialized this workflow to have the name asset transfer, and this also has a display name of asset transfer with a space. We give a description for this workflow as well, and we then specify in the initiators field that an instance of this particular workflow can only be created by someone who has the user role. We then also say that the start state or the initial state of the workflow will be active. Note that an instance of this workflow will represent an asset in our application. And even in the constructor in our smart contract, we initialize the asset to be in the active state, which takes us along now to the property section. And this is where we will need to map the different fields in the underlying contract to properties within this config file. For example, we have a variable called state within the fields of our contract, and we have a similar corresponding property called state within this config file as well. Similarly, we have a property corresponding to the description field in our contract. The presence of these properties in the config file will ensure that the values of the contract fields will be available in the web UI of the blockchain Workbench app. Note that in the type field for each property, we can specify whether it's a state or a string. And we move along now to another property for the asset applicant. And this is not highlighted here, but you can see it in the bottom of the page. And in this case, the type has been marked as user. So this asset applicant has been mapped to one of the roles in this config file. The same also applies to the next property, which is for the asset inspector, and the type here is marked as inspector. We also have a field for the asset owner, whose type is user. And then we move along and describe the constructor for our application, where we specify the details of the parameter to the constructor. In our case, since there is just a single parameter, we specify the name, the description, the display name, as well as the type for the parameter. And again, the presence of this in this config file ensures that we will be able to call the constructor from the web UI. This is something which will happen when we initialize an asset. We move along now to the function section. So just like we have properties within the workflow, which need to map to the fields in our smart contract, the functions of the workflow need to map to the functions in the contract. Again, the inclusion of the functions here will allow the invocation of those functions from the web UI. So here we have a reject function, and we describe this with a name, a display name, a description, and the list of parameters. And we do the same for the accept offer function. In this case, though, we can specify the details for the parameters. Moving further along, we also include the definition for the terminate function, and then there is one for the request function as well. and one also for the mark inspected function. These three functions do not include any parameters. While all of this seems a little mechanical, the interesting part of the workflows is actually in the state definitions. This is where we will define the different states which our asset can be in, and then we will also define the transitions which are possible from each of those states. So we begin with the definition of the active state. We include a display name, a description, and we can also have a %complete field. And there is also the style field, which represents whether this particular state represents a successful state or a failed state. Since being in the active state is certainly not a failure, we will mark this as success. Which takes us along now to the transitions from the active state. So there are several fields which define a transition. In the case of the first of these transitions, this is the one which will occur when someone invokes the terminate function, and this is specified in the function field. When the terminate function is invoked, the next state for the asset will be terminated. And note here that we can specify a number of different states in a list. The other fields of interest are the allowed roles fields, where you can specify the list of roles defined within this config file, which can initiate this transition. And then the allowed instance roles are roles defined within the contract, which can initiate the transition. So it is only the asset owner who can initiate the terminate function. We also define a transition for the request function, in which case the asset moves from the active state to the offer place state. And that is a transition which can only be invoked by someone marked as a user. We move along now to the next state, and this is for the offer placed state. The %complete at this point will be marked as 70, and we have three different transitions which are possible from this state. If the offer has been placed and then the owner of the asset accepts the offer, then the asset will transition to the pending inspection state. On the other hand, if the offer is rejected, and this is also triggered by the asset owner, then the next state will be active. Also, if the asset owner invokes the terminate function from this state, then the asset will move over to the terminated state, which moves us along now to the next state for our application, which is pending inspection. And on this occasion, there are two possible transitions. If the mark inspected function is invoked, then this asset will move along to the active state. On the other hand, if terminate is invoked, it will move to the terminated state. And finally, we have a definition for the terminated state. And on this occasion, there are no transitions which are possible. And also, the type field is marked as failure because this can be considered a failed state for the asset. So we have now taken a look at both the smart contract source file as well as the configuration file, which defines our application. In the next video, we will initialize our blockchain application on the Azure Blockchain Workbench by uploading both of these files. Now that we have defined a config file along with a Solidity source file, we can use those in order to instantiate a blockchain application on the Azure Blockchain Workbench. We are back in the dashboard for the Blockchain Workbench, and we have this menu up on the right where we can upload the config file along with the Solidity source file. This menu can be brought up by clicking on the New Application button on the main dashboard. So let us go ahead and upload the JSON file which it is asking for. So we can click on this Browse button and then navigate on the file system to where the asset transfer.json file is located, and then select it. You can go ahead and upload that file. Once that config file has been uploaded, we will have the option to upload the Solidity source file, and then we click Browse again. And then on this occasion, we will select the asset transfer.sol file. Alright, so we now have the config file along with the accompanying Solidity source file up, and it's now time to create an instance of our blockchain application out of these two files by hitting the deploy button. And with that done, our asset transfer application has been created and deployed on the blockchain workbench. However, this app is not yet ready for use because there are a few details which we need to provide in order to instantiate this application. One of the steps involves assigning members to the different roles we have created in our application, but this is something we will do just a little later, since we can now take some time to explore this dashboard on the blockchain workbench. So once we close out this notification, we can go ahead and check this box at the top right for our deployed app, and this in turn will enable some of the buttons available at the top. From here, we can view the different versions of our application by clicking the versions button. And of course, there is just version 1.0 which has been currently deployed. But if you go ahead and deploy additional versions, you will see the entire list right here. Now, if you'd like to create a new version of this application, let's just say you have modified the underlying Solidity source file or the config file, then you can upload this new version by clicking the Add Version button and then uploading the two files from this interface. So we won't be doing that right now, so we can just close out of this page. And then following that, we will explore the option to disable this application. So for example, if you have found a bug in the application and you'd like to disable the app to prevent users from using it until a new version has been developed, then you can disable this application by hitting this disable button once the app has been checked. So you'll notice that the app has disappeared from this dashboard, and that is because this current dashboard is for the enabled applications in our blockchain workbench. And this fact is obscured by this notification in the right, so I'm just going to close this down. And yes, you can see that this is for the enabled applications. And to view the disabled ones, we just expand this drop down and select disabled applications. And this is where we can view the asset transfer app which we have just deployed. In order to re-enable this, we can just check this box and then hit the enable button. So now that our app has been enabled once more, it is time for us to instantiate it. So we head back from this disabled apps menu over to the one for enabled apps. And then from here, we will need to add additional members to this application. So you can either use this particular menu to do that, or alternatively, you can check the app and then proceed to this members list at the top right. The one listed member for this app is the user we are currently logged in as on the Azure portal. But this member has not been explicitly added, so when you click on this, you may see the membership go down to 0, and then from this interface, we will be allowed to add additional members. This is where we can assign some of the users which we created on the Azure Active Directory as members for this blockchain app, and while doing so, we can assign them specific roles. So to do that, we can just click this Add Member button, and this will bring up a text field where we can specify the name of the member we wish to add, and this will have an autocomplete feature which will pick up the accounts from the Azure Active Directory. So in order to enter the details of Alice, we just begin typing Alice, and then we select that user which comes up in the auto suggest. And now in order to assign Alice a role in this blockchain application, we have this drop down menu and the two roles which we defined within the config file. Those of the user and the inspector are the options which are available for us. And this is where we will assign Alice to be a user for our app. And once we hit add, Alice is now a bona fide member of this asset transfer application. Now Alice is in a position to create assets and also be in possession of them. However, in order for us to display the transfer of assets, we need an additional user, for which we will go ahead and add a second member. Now this is going to be the user Bob, so I'm going to type that and select it from this auto suggest list. And then for the role for Bob, we can also assign him to be a user. With the selection made, we hit add, and now we have two members in our blockchain application. So Alice and Bob are both users, which means that they're capable of being in possession of an asset. However, in order for us to transfer an asset from one of these users to the other, we will need the approval of an inspector. And this is where we will go ahead and create an additional member for our application. As for the particular identity of this member, I'm going to use the account which I'm currently logged into Azure as, which in my case is cloud.user. So once this user selection has been made, I'll just go to the drop-down and select the role of an inspector. Following that, I'll just hit the Add button. And with that complete, we now have 3 different members for our blockchain application, 2 users and 1 inspector. At this point, we are ready to instantiate this application and then record transactions on it. And for that to happen, we need to create a new instance of a workflow out of this deployed app. And that is something we will do in the next video. So for now, I'll just close out of this menu and then I'll uncheck this application. So far, we have initialized and then deployed our blockchain application on the blockchain workbench on Azure by uploading a config file along with an accompanying Solidity source file. Following that, we assign members who can use this application, and this is where the fictitious accounts for Alice and Bob, which we created earlier on in the Azure Active Directory, were assigned members to this application with the specific role of a user. We also assigned an inspector role to one member. Now, given that this is supposed to be an asset transfer application, what is the asset which will actually be transferred? Well, to do that, we will now need to initialize an instance of a workflow. And for that to happen, we can now click on this deployed application on the Azure Workbench. So when we do that, we will be directed to a new page where all of the workflows associated with this application will be visible. And given we haven't really set up workflows yet, this page is currently blank. In the context of the Azure Workbench, an instance of a workflow is considered a contract. And in our case, one contract will represent an asset, which of course can be transferred between different users. As defined in both the Solidity source file and also our config file, there are different fields which represent an asset, and those are all visible on this page as the column headers. So this includes an ID, a state, a description, the asset applicant, and so on. So if you don't wish to view all of these fields on the page, then you can hit this button to customize the table. And this will bring up all of the fields which are visible on the page. But you'll observe that only some of these can actually be removed. These include the ones which we explicitly defined within our contract and config file, such as the state, description, as well as the applicant, inspector, and owner of an asset. And the ID, modified, and modified by fields are those which are handled by the blockchain workbench itself. We won't be modifying any of these columns, so we can just hit cancel here. And then you'll observe that there is no option here in order to initialize a new workflow. And this is because the user we are currently logged in as, which in my case is cloud.user, happens to be an inspector. And the way we had set up this application, an inspector does not have the ability to initialize a workflow. We need to be logged in as a user in the context of our app. To do that, I'm going to log in as the member Alice, and for that, I will sign out as cloud user. This signing out could take a couple of seconds, but once that is done, you will have this "You've signed out" notification. At this point, you could be automatically redirected to a sign-in page, and if not, you can connect to the Azure portal. And then on this occasion, I won't be signing in as the cloud.user, of course, but will sign in as another account. For the user Alice, the ID which I had created was alice@lunicorn.com. And then following that, we will be prompted to enter the password. And this was one of the details which I had saved previously in a text file. So I'll just bring up the file and then copy over this password right here. Since I'm logging in as Alice for the first time, we will be prompted to update the password, which I will just go ahead and do. And once we sign in, we'll be taken directly to the Azure Workbench. And if not, you can navigate to it from the Azure portal. But from the Workbench, we can see the applications which are available to the user Alice. And as of now, she has membership to just a single blockchain application, which was the asset transfer app, which we had deployed previously. When Alice clicks on this app, she is directed to the same workflows page. But given that Alice has the role of a user with this asset transfer app, there is a button in order to create a new workflow instance, that is, a new asset. So let us go ahead and create this new asset. And this one will represent, let's just say, a company car. And this will be a Volkswagen Polo GT. This is the value provided as the description for this asset. And this also represents the field which is the parameter supplied to the constructor of our contract. So we can assume that both Alice and Bob are salespeople in an organization who can make use of a company car in order to go and visit their clients. Access to the car is of course regulated by the logic which we have defined within our blockchain application. And any transactions with regards to this car, including its transfer to another employee, will be recorded on the blockchain. So now that we have defined this particular asset to represent a car, which is a Volkswagen Polo GT, we will click on the Create button in order to create this new contract, which is an instance of a workflow in our asset transfer app. So once we close down this notification, all of the details of our asset will be available right here. So you can see that the initial state of this particular car is active, just as we had defined within the source code of our application. Within the Solidity source file and also the config.json file, we had specified the other fields which are populated when an instance of the asset is created. This includes the asset owner and also the description which we have just supplied. So now that our asset has been initialized, we can click on it in order to view the different operations which are permitted with this asset. So this has automatically been labeled as Asset Transfer Contract 1. And you can observe that this need not necessarily represent a car, but pretty much any asset which you may imagine belongs to this organization. Since this is an instance of the workflow, which of course involves a number of transitions which will take this asset from one state to another, there are a number of actions which can be taken in order to prompt the transitions. So here we have seen one of the actions which has already been recorded, and this is where the user Alice Doe has created this asset by effectively calling the constructor defined within our Solidity source file. So we can now invoke other operations by hitting this Take Action button. And when we do that, all of the operations which Alice can perform as someone who has been assigned the role user for this application will be available from this interface. So at the top, you can see that the current contract state is active. And within the config file, we had defined this active state to have two different possible transitions. To view those transitions, we can expand this dropdown, and these include the option to terminate the contract or in order to make a request. Only someone who has the user role in the application will be able to trigger this request function, but it doesn't really make sense for Alice, who is already the owner of this asset, to put in a request. So we can just cancel out of this interface and then continue exploring this dashboard for the asset. All of the details for the asset can be viewed right here, including the location to which the contract has been deployed, as well as the various fields which are part of the smart contract. Once we're done exploring this particular asset, we can head back to the asset transfer section in order to take us back to the main workflows page for our application. So by logging in as this member Alice, who has the user role in our application, we were able to create a new instance of this asset, which in this context of the blockchain workbench can be termed a new contract. To continue testing its functionality though, we will need to invoke an asset transfer. And for that, we will need to sign out as Alice. And then in the next video, we will log in as Bob and then put in a request for the transfer of this car asset. In the previous video, we logged in as the member Alice and then proceeded to create an instance of our asset, which happens to be a company car. Now, Alice is currently assigned as the owner of the asset, and we will now test the functionality where another employee, in our case Bob, will be able to put in a request for this company vehicle. Since we are currently logged in as Alice, we will need to sign out. So I'm just clicking on this button in the top right, and then we'll click sign out. Alice is now signed out of Azure, and now we will sign in as the user Bob. So I'll choose to use another account to log into Azure, and the ID we created for Bob, in my case, was bob@lunicorn.com. As for the password which was generated, I have saved that down in the text file, so I'll copy that over and paste it right here. And then when moving to the next screen, we will be prompted to update the password for this user. I'll just go ahead and enter a new password and then click sign in. And we are now signed in as the user Bob to the Azure Blockchain Workbench. Bob, of course, only has the permissions to view one application, which is the asset transfer one. And when we click on it, Bob is able to view an instance which we created of that application, namely the asset for the company car, which is a Volkswagen Polo GT, which was created previously by Alice. Now, in order to interact with this asset and put in a request to get possession of it, Bob will need to click on this particular instance, and then using the interface, we'll have the ability to take some action. So when we click on this button, a menu similar to what we saw previously pops up, and of course, the description of the asset is available here. But when we expand the drop-down to see the available options for this user, there is just one transition which this user can invoke. And this is where a request can be put in for the application. Alice, on the other hand, had the ability to invoke not only a request function, but also the terminate function. However, if you observe the asset transfer.json file which we deployed, under the transitions from the active state, we define that the terminate function can only be invoked by someone who is the asset owner. Since Alice is currently the owner of the asset, Bob does not have the ability to invoke the terminate function. However, he can put in a request. So we will now make this selection and then click Take Action. When that is done, this might take a few seconds, but you will observe that our action has been recorded successfully on the blockchain. So we close down this notification and move over to the status section, where we will observe that the contract is currently in the offer placed state. We can now head back to the main asset dashboard, and you'll observe that the asset applicant field for this has now been updated to include the name Bob. Under the state column, you'll also notice that it is now in the offer placed state. So we have now successfully recorded a request for this particular asset after signing in as Bob. In order for the asset transfer to go through, however, the current owner, namely Alice, will need to approve that transfer. And for that, we will go ahead and sign out as Bob. So clicking on this button in the top right and then clicking sign out, Bob is now no longer logged in to Azure. And we will once again choose to sign in, and this time as Alice. So we will just click on this instance of the application. And of course, Alice is able to view the updated status, which includes the fact that Bob has now put in a request for this and that it is in the offer placed state. And by clicking on this instance, the transitions are visible in this section. And then we can also observe that the latest action was when the user Bob called the request function. When we click on Take Action, we can view the updated state. But when we expand this menu, Alice now has not two, but three different options. She can choose to accept the offer, reject the offer, or to terminate the asset. These are the three functions which we defined within the transitions from the offer placed state within the asset transfer config file. Let us now assume that Alice chooses to reject this offer from Bob because she currently wants to continue using the car. And then we click on Take Action. Once that is done, you'll observe that this particular action was also recorded successfully on the blockchain. And we can view in this activity section all that has transpired with this particular instance of the car asset. The status section records the fact that there is a third action which has been recorded for this asset and that it is currently in the active state. And then, of course, we can head over to the details in order to view information such as the current asset owner, which of course is still Alice. With that done, we can head back to the dashboard for a particular application. And you'll observe that the asset applicant field has been cleared and that the state of this contract is now active once more. So we have now successfully tested out the reject function for our application, and we can proceed with the tests where we will record one more request for this car, and on that occasion, Alice will approve the request. Following the deployment of our application, which represents the transfer of assets, we initialize such an asset which represents a company car. This car is currently assigned to the employee Alice, and then later on, we triggered a request for that car by the user Bob. Alice went on to reject that request, but it is now time for us to invoke another request for that same asset, and we will do that as the user Charles. You will recall that Charles has not been assigned as a member to our asset transfer application just yet. So we will see what exactly Charles sees when that user signs in to the Azure account. We will first need to sign out as Alice. So I'm now going to navigate to the top right and then sign out. And once this is done, it is time to sign in as the user Charles. So I'll just choose the option to pick another account to sign in as. The ID for Charles I had set to charles@lunicorn.com. And of course, the password was something which I had saved in this text file. So copying that over and then signing in with these credentials. We will be prompted to update the password. Once that is complete, the account Charles is connected to the Azure Blockchain Workbench. You'll observe that no applications have been associated with this user just yet. And of course, this is because Charles has not been added as a member to the application which we had deployed. So you need to be explicitly given membership in order to be able to interact with the application, as illustrated by this particular user signing in. To fix that, and for Charles to be able to put in a request for the asset, which is our car, we will sign out as Charles. And we will then need to sign in as a user who has the ability to add a new member for this particular blockchain application. And in my case, that is the user who deployed the application, and that is cloud.user. So you will need to sign in as your own account, which you had used initially. Once you are logged in, we can modify the membership of this application. And for that, we will first need to select it by clicking on the checkbox and then heading over to the top right. Even though we can observe 4 members here, this will reflect correctly the 3 members who currently have access to this application when we bring up the menu. So on this occasion, the correct membership number is visible. So we click on it once more, and we will choose to add a new member. In the form which appears, we can search for the user Charles and then make use of the autocomplete here. And with the selection made, we will select a role for Charles, who, like Alice and Bob, will also be a user. So with that selection made, we can hit add. And now we do indeed have 4 users who are members of this particular application. At this point, we can close out this membership menu, and we can also uncheck this box next to asset transfer. So now that we have made the changes to our application, we no longer need to be logged in as this user. So we will sign out. And this time we will sign in as Charles and will expect to see this instance of the application visible to us. So entering the credentials here, I'm going to sign back in. And on this occasion, the blockchain workbench does include the asset transfer application for Charles as well. When we click on it, the deployed instance of the application is visible. And then when we click on this as well, we observe the latest state of this asset. So it's currently in the active state. And we also have the ability to take action and invoke one of the transactions. And of course, all the latest activity is also visible here. We can now go ahead and trigger a request for this asset. So when we click on Take Action, the menu comes up. We head over to the drop-down menu and then select the one and only option available to us, which is to make a request for this asset. With the selection made, we click on Take Action, and the request put in by Charles for this vehicle has gone through successfully. And we can also confirm that the status for this particular vehicle asset has now changed to offer placed. And yes, even in the activity section, the fact that Charles has put in a request for the asset has been recorded. All of these details are now reflected on the blockchain. So we head over now to all of the instances of the asset, and the details have now been updated so that Charles appears as the asset applicant. All right, for this transfer to go through, we need to sign in as Alice and accept the offer put in by Charles. So once again, we will go ahead and sign out as Charles. And then we will sign in this time as Alice. Back to the blockchain workbench, we click on the deployed application, which of course there is just one instance of. And then when we click on this vehicle, logged in as Alice now, we observe that Charles has put in a request. And now to take action on our own as Alice, we click on this button and then head over straight to the drop-down menu, where we will now choose to accept the offer put in by Charles. So this is the second scenario we are testing out when a request has been made for the asset. So we click on Take Action. And if you bring up your Solidity source file, you will observe that this triggers a call to the accept offer function. And that function requires an argument to represent the inspector of this offer. You can think of the inspector for this offer as being some kind of supervisor who needs to give the go-ahead for the transfer of the asset from Alice to Charles. And in the case of Alice, she will need to supply the name or the details of the inspector. Within the Solidity source file, you will observe that this parameter needs to be in the form of an inspector's account address. However, when using the Azure Blockchain Workbench, we only need to specify an Azure Active Directory account, which will be mapped over to an address automatically by the application. Another factor to consider is that the inspector which we assign right now needs to be assigned the role inspector rather than the user in the context of our application. Only then will the asset ownership actually transfer over to Charles. Given that in my case, I have assigned that inspector role to this cloud user, I'm going to select that. And following that, we will go ahead and click on Take Action. And we are notified that this particular action has gone through successfully. And this is reflected in the status of this particular asset, which has now moved along to pending inspection. We will also observe within the activity section that Alice has accepted the offer put in by Charles. And to view the details at a higher level, we click over to the asset transfer instances. And yes, we can view that the asset applicant is Charles. The asset inspector has now been populated to be cloud user. And the state is also now updated to pending inspection. The asset owner, though, is still Alice Doe, since the inspection needs to be passed by cloud user in my case in order for Charles to become the new asset owner. So I'm now going to sign out as Alice Doe and then sign back in as cloud.user who is the inspector of the asset transfer. In the previous video, the user Alice approved the request coming in from Charles for a transfer of the asset, which in our example is a company car. When accepting the offer, Alice had to select an inspector who will need to approve this transfer in order for Charles to become the new owner of the vehicle. The inspector, in my case, is the user cloud.user. So I'm now going to sign back into Azure using the credentials of that account. So from this dashboard for the blockchain workbench, we click on our application. And then when we click on the instance of the application, this particular user will need to take some more action in order for the asset transfer to go through. So we click on that button. And from the menu which pops up, we can see who the inspector is currently for this instance of the application. And then heading over to the drop-down menu, the two possible transitions from this pending inspection state, specifically the functions to mark this particular asset transfer as inspected and the terminate function, are both available here. The inspector will approve this request for the transfer of the asset from Alice to Charles. So we select Mark Inspected and then click Take Action. This particular action has also gone through successfully, as reflected in the status for this particular asset, which is now back to active. And we can view this latest activity in the activity section as well. And then heading back to our asset instances page, we observe that the status has indeed been updated to active. And very importantly, the asset owner is now the user Charles. As defined within the mark inspected function in our Solidity source file, the asset applicant field has effectively been cleared, and the asset inspector is still cloud.user for me. We will now play out another scenario where the user Bob puts in another request for this particular car. So we can sign out as this user, and then we will sign back in as Bob. So once we are in the dashboard, we will click on the application, and then clicking on this instance, we will head right to the Take Action button. And just like we did previously with the user Bob, we will now put in a new request for this particular asset. And when we take this action, the status reflects that an offer has been placed for this vehicle. Heading back now to the instances of our application, we can view all of the details for the different fields in our contract. And we can also see the fact that the asset inspector is cloud user. So now in order to approve this offer from Bob, we will need to sign in as Charles. And let us do just that by first signing out and then connecting back as Charles. So from the dashboard for Charles, we will click on our application, bring up the instance of our deployed application, which is the Polo GT vehicle, and then go ahead and take action once more. This time, of course, we will accept the offer to transfer this vehicle over to Bob, since we assume that Charles has no more use for the vehicle. And when we hit Take Action, we will be prompted to enter the details of the inspector. We can get Charles to select the same inspector as Alice did, which in my case is cloud user. So once that selection has been made, we can hit Take Action. And now this asset has gone over to the pending inspection state. At this point, it helps to go ahead to the activity section and then view the full history of activities on this particular asset. Right at the very top, though, we will have recorded the fact that Charles has accepted the offer. So we move back to our instances view, and all of the details of the vehicle are now available right here. So it is now time to log out as the user Charles, and we will log in as the inspector, which again, in my case, is cloud.user. I'll just go ahead and enter the credentials once more. And then from the dashboard, click on the application. And following that, we'll bring up the instance of our deployed app. And then head over to take action, where the inspector can examine some of the details, including the fact that the latest action on this particular contract has been by the user Charles, where he accepted the offer. And then heading over to the drop-down menu, out of the two options available here, the inspector will choose to terminate this particular asset. So Bob is just never going to get this vehicle. And this is the only function in this contract which we haven't quite tested out yet. So we will now call this terminate function as the inspector. And the conditions to invoke this terminate function include that the one invoking it should not be both the asset owner and the asset inspector. The user we are currently signed in as is only an inspector and not the asset owner, which is why this invocation will be possible. But in a more realistic application, you may have an entirely separate role in addition to the user and inspector, who will have explicit permissions to terminate an asset. For now though, we can just hit take action and then record the fact that this terminate transaction has gone through successfully. So the status has changed once more, and we observe that there have been a total of 9 transitions which have been recorded. The latest one being a call to the action terminate. An important detail to note though is under the action section in this dashboard. There is a message which says that there is nothing for you to do right now, and this is because this asset has been terminated and there are no possible transitions from that state, which is why we cannot take any more actions on this particular asset. So I will now close out this notification and head over to the instances of our contract. And then from here, we observe that the state is now terminated, and we still see the details of the asset applicant and the asset inspector right here. So when we are connected as the user, we saw that there are no more actions which are possible on this asset. And for completeness, let us now sign out as this particular inspector. And then we will sign back in as one of the other users of this application. And then check out what actions are possible from there. So I'm now going to reconnect to the blockchain workbench as the user Charles. I'll enter the credentials here. And then following that, we head over to our application instance. And then we click on it and bring it up. And once more, the action section is empty. So even as a user, as opposed to an inspector for our application, we are unable to take any further actions on this asset. However, for bookkeeping purposes, all of the activity which has been recorded on this asset is still available on the blockchain. And we can view all of the details right here in this dashboard. Now, if you'd like to create a new instance of a vehicle or any other company asset, we can head back to the instances of our asset transfer application, and then go ahead and create a new instance by hitting the new button. Once you do this, the menu of course will pop up where you can instantiate a new contract, that is a new instance of a workflow, which of course will call the constructor for our application, which needs a description as an argument. Once you do that, you will have created a brand new asset and you can interact with it just as we have done so far, where the users Alice, Charles, and Bob already have permissions since they are members of the app. We don't need to do that once again though, so we can just cancel out of this. And with that, we come to the end of this demo on the Azure Blockchain Workbench. In this exercise, you will start off by describing workflows in the configuration file for an Azure Blockchain Workbench application. During this course, we defined a blockchain application which enables the transfer of assets between employees in an organization. And to do that, we defined a workflow in order to facilitate this transfer of assets. This workflow, though, involve multiple different components, and you will need to recall what exactly they are and what purpose they serve. Next, you will list down the characteristics of roles in an Azure Blockchain Workbench app. Within the config file which we defined during the course, we also listed two different roles which will apply to different members who use the blockchain application. You will need to recollect how exactly these roles are defined and what effect they have on how users can use the blockchain application. Each of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task in the exercise, you needed to describe workflows as defined within the config file of an Azure Blockchain Workbench application. At a high level, a workflow defines a collection of states and actions for the application, along with transitions which are triggered by specific actions in certain states. When defining workflows in the config file, we can start off by defining the name, the display name, and a description for the workflow. And following that, a workflow includes a number of different properties. Since a config file is tightly bound to the underlying contract in an application, the properties need to map to the fields defined within that contract. This will enable the values of those fields to be displayed in the Blockchain Workbench UI. In addition to the properties, there are also functions which make up a workflow. And once again, these functions need to map to the functions defined within the underlying smart contract. Workflows are also defined by a collection of initiators, which include the different roles in the application, which have the capability of initiating workflows. Once a workflow has been initiated, it is capable of transitioning between multiple states, which again are defined within the workflow. When initiated, a workflow is assigned a start state, and then following that, each state also has a collection of associated transitions. These represent the different transitions which are possible from that state, and the definition of the transition includes the function which can trigger the transition, as well as the destination state for that transition. So all in all, by means of the states and the transitions, as well as the functions and properties, a workflow defines the different stages which can be reached by a blockchain application, along with the means by which the stages can be reached. Moving along now to the next task in the exercise, which was to list down the different characteristics of roles as defined within the config file of a blockchain app. So a role, as we saw during this course, is something which is specific to an application defined on the Azure Blockchain Workbench. The roles will determine which members have the permissions to initiate specific actions on a blockchain workbench application. These application roles are defined within the configuration file, and initially they only require a name and a description. It is within the definition of the workflows for an application where the roles are applied, where you can define, for example, that a specific transaction can only be initiated by certain roles. So this is how roles effectively determine the degree of access for different members in a blockchain application. For this to work though, the individual members who have access to the blockchain app need to be assigned specific roles, and this is something which occurs at the time of initializing the application.